Hello there, and welcome. Tonight I want to take you somewhere special, somewhere that exists both everywhere and nowhere at once. It's a place that surrounds you right now, fills the space between your thoughts, and dances in the darkness behind your closed eyelids. As you settle in, perhaps adjusting your pillow just so, letting your shoulders sink a little deeper into whatever surface holds you, I want you to consider something remarkable. You're about to embark on a journey into one of the universe's most elegant mysteries, a secret that governs everything from the breath you're taking right now to the light of the most distant stars. Listen to the quiet around you. Perhaps you hear the gentle hum of electricity in the walls, the distant murmur of traffic, or maybe just the soft rhythm of your own breathing. Whatever time it is where you are, whether it's late evening with the last traces of sunset fading from your window, or deep in the night when the world feels hushed and still, you've chosen this moment to explore something profound. And I'm curious, where are you listening from? Are you tucked into bed in a bustling city, or perhaps in a quiet suburb where the stars peek through? Maybe you're in a small town where the night sounds are dominated by crickets and wind, or even somewhere completely unexpected. Whatever corner of our planet you occupy right now, you're connected to the same fundamental rules, the same quantum dance that we're about to explore together. Before we dive deeper, let me invite you to make yourself even more comfortable. If you enjoy these journeys through the hidden architecture of reality, these gentle explorations of physics that wash over you like a lullaby, consider following along for more. There's something special about building a collection of nights like this, each one peeling back another layer of the universe's mysteries. You might like to subscribe or follow, not because I'm asking you to do anything urgent, but simply because next time, when sleep calls and curiosity whispers, we can drift even further together into these profound questions. Think of it as leaving a bookmark in the cosmic library, a gentle reminder that these explorations are here whenever you need them, whenever the day has been long and your mind seeks both rest and wonder in equal measure. Now let your awareness expand gently from where you are. Feel the weight of your body against the bed or chair, the subtle pressure of gravity that has held you since birth. This same force that keeps you grounded extends outward, weakening with distance but never truly disappearing, connecting you to the earth below, to the moon that might be visible through your window, to the sun sleeping on the other side of our planet, and onward to every star you've ever seen or imagined. Each point of light in the night sky is a sun, perhaps with its own worlds, its own quiet nights, its own mysteries unfolding in the darkness. But tonight, we're going to journey inward as well as outward. We're going to shrink our attention down past the familiar scale of everyday objects, past the texture of your blanket, past the weave of its fibers, past the long chain molecules that give those fibers their strength, down to the atoms themselves. And here, in this realm so small that 1 billion of them could dance on the head of a pin, we encounter something that challenges everything our everyday experience tells us about identity, about things being separate and distinct. You see, in your daily life, everything has its own identity. The cup on your nightstand is distinctly different from any other cup, even if you bought 2 identical ones from the same store. You could, if you wanted, mark one with a tiny scratch, follow it through its life, know that this specific cup was the one you drank from last Tuesday. The pillow under your head might look exactly like its partner on the other side of the bed, but you know which one is yours. You've shaped it with countless nights of sleep, and even if someone switched them while you weren't looking, there would be subtle differences. A particular way the filling is compressed, a faint scent that belongs to you alone. This is how we understand the world at our scale. Everything is separate, trackable, unique in some way, even if that uniqueness is subtle or hidden. 2 identical twins might fool strangers, but they know who they are, and those who love them can tell them apart. 2 snowflakes might look similar from a distance, but under a microscope each one reveals its own crystalline autobiography, a unique story written in ice about its journey through the clouds. But as we descend into the quantum realm, something profound shifts. Down here, in the domain of electrons and photons, of quarks and neutrinos, identity as we understand it begins to dissolve like morning mist. Imagine 2 electrons. Not just similar electrons, not electrons that look alike or behave alike, but 2 electrons that are absolutely, fundamentally, impossibly identical. There is no test, no measurement, no observation that could ever tell them apart. They don't have little quantum serial numbers, they don't carry the history of where they've been, they don't age or wear or develop character. They are perfect copies in a way that nothing in our macroscopic world can be. This might not seem particularly strange at first. After all, we're used to thinking about things being very similar. But the quantum identical goes beyond similar, beyond even what we might call exactly the same. It enters a realm where the very concept of this one versus that one loses all meaning. If you could somehow grab two electrons and switch their positions, not that you could actually grab them, but imagine you could, the universe wouldn't notice. Not because the universe isn't paying attention, but because there is literally no difference to notice. The switched configuration is not just similar to the original, it is the original in every meaningful sense. And here's where our journey tonight truly begins, where the mystery deepens and beckons us forward. These identical particles, these perfect quantum twins that populate our universe by the countless trillions, don't just exist in a state of perfect similarity. Their identical nature forces them to follow different rules than anything we experience in daily life. They split into two great families, two fundamental categories that govern how matter and energy behave at the deepest level. The first family we call Bosons, named after the Indian physicist Satyendra Nath Bose, who, along with Einstein, first understood their strange behaviour. Bosons are the social particles, the ones that love company. They include photons, the particles of light that might be streaming from your bedside lamp right now, or perhaps filtering through your window from a streetlight or the moon. They include the W and Z bosons that mediate the weak nuclear force, the gluons that hold atomic nuclei together, and if our theories are correct, the gravitons that carry gravity itself, though these remain hypothetical, whispered about in equations but never yet directly observed. Bosons have a remarkable property that emerges from their identical nature. They can share the same quantum state. In fact, they prefer it. The more bosons you have in a particular state, the more likely additional bosons are to join them there. It's as if they're attracted to crowds of their own kind, creating a kind of quantum peer pressure where being in the same state as others makes that state even more attractive. This is why laser light is possible. Countless photons all marching in perfect synchronization, sharing the same energy, the same direction, the same phase, creating a beam of unprecedented purity and power. The second family we call Fermions, named after the Italian physicist Enrico Fermi. These are the loners of the quantum world, the particles that insist on their own space. Electrons are fermions, as are quarks, the building blocks of protons and neutrons, and neutrinos, those ghostly particles that stream through you by the billions every second without interaction. Fermions follow what we call the Pauli exclusion principle, named after Wolfgang Pauli, who first articulated this rule. No two fermions can occupy the same quantum state. They absolutely refuse. It's not that they don't want to, wants and desires don't exist at this level. It's that the mathematics of the universe, the very fabric of reality, forbids it. This fundamental difference between bosons and fermions shapes everything we see and experience. The chair you're sitting or lying on is solid because electrons, being fermions, refuse to be squeezed into the same space. The atoms in your body maintain their structure because electrons arrange themselves in shells, each one finding its own unique quantum state, building up the periodic table element by element. Meanwhile, the light by which you might be reading or the soft glow of your phone screen is possible because photons, being bosons, can crowd together in vast numbers, creating the classical electromagnetic waves we perceive as light. But here's the beautiful mystery we're exploring tonight. Why? Why does the mere fact of being identical force particles into these two distinct categories? Why can't there be particles that sometimes share states and sometimes don't? Why is the universe so strict about this division, so absolute in its sorting of particles into these two fundamental types? The answer lies in something called exchange symmetry, a concept so subtle and profound that even physicists who work with it daily sometimes pause in wonder at its implications. When we write down the mathematical description of two identical particles, what physicists call the wave function, we have to account for the fact that switching the particles doesn't create a new physical situation. The mathematics has to reflect this indistinguishability, and it turns out, through a beautiful piece of mathematical reasoning that we'll explore gently tonight, there are only two ways to do this consistently. For bosons, when you exchange two particles in the mathematical description, the wave function remains exactly the same. It's like writing a sentence where swapping two identical words doesn't change the meaning at all. The universe shrugs at the exchange, continues on without missing a beat. This is called symmetric exchange. For fermions, when you exchange two particles, the wave function picks up a minus sign. It's subtle. The physical probabilities which depend on the square of the wave function remain the same, but that minus sign has profound consequences. It means that if you try to put two fermions in the same state, the mathematical description cancels itself out. Become zero says this cannot be. This is called antisymmetric exchange. What's remarkable is that these are the only two possibilities. You might think there could be particles that pick up other phases when exchanged, not just +1 for bosons or -1 for fermions, and in two-dimensional systems there are indeed such particles called anyons, which we'll touch upon later. But in our three-dimensional world, the mathematics is unforgiving. Bosons or fermions, social or solitary, plus or minus, there is no middle ground. As you lie there in the darkness, perhaps you can feel the truth of this division in your own body. The fermions, the electrons and quarks, maintaining structure, keeping things separate and organized, building the architecture of atoms and molecules. The bosons, photons of infrared light radiating from your warm skin. W and Z bosons mediating radioactive decays in trace elements. Within you, virtual photons carrying the electromagnetic force between charged particles, flowing and overlapping, carrying forces and energy without restriction. Consider your breath for a moment. The air you're breathing is mostly nitrogen and oxygen molecules, held together by electrons shared between atoms. Those electrons, being fermions, carefully arrange themselves in molecular orbitals, each finding its own quantum state, never overlapping perfectly with another electron in the same state. But the gentle warmth you feel in your breath, that's carried by photons, infrared photons that can pile together by the countless billions, all sharing similar energies, creating what we experience as heat radiation. This division between bosons and fermions extends far beyond your body, far beyond your room, beyond Earth itself. In the hearts of stars, fermions in the form of protons made of quarks resist being squeezed too close together, their quantum pressure fighting against gravity. But the light produced by fusion, the photons that carry energy from the core to the surface and then across space to warm distant planets, these bosons flow freely, overlapping and combining without restriction. In the spaces between stars, in the vast cosmic voids that make up most of our universe, both families of particles drift in unimaginable solitude. Lone electrons, stripped from long-destroyed atoms, travel for millions of years without encountering another particle. Photons from the cosmic microwave background, the afterglow of the Big Bang, have been travelling for nearly 14 billion years, carrying information about the universe's infancy. These bosons pass right through each other when they meet, ghostly ships in the cosmic night, while fermions would have to find their own separate paths, their own unique states. Even in the densest places in the universe, this fundamental division holds. In neutron stars, where a teaspoon of matter weighs as much as a mountain, fermions in the form of neutrons are packed to the absolute limit allowed by quantum mechanics. They resist further compression with a pressure that comes not from temperature or motion, but from the simple fact that they are fermions, that they cannot share states. This degeneracy pressure, as physicists call it, holds up the star against its own gravity, creating an object so dense that atoms themselves have been crushed out of existence. Meanwhile, in those same neutron stars, neutrinos, those ghostly fermions that barely interact with matter, stream outward, each finding its own quantum state, never overlapping with another neutrino in the same state. And photons, carrying away the star's heat, crowd together in vast numbers, their bosonic nature allowing them to create the intense radiation fields that surround these cosmic lighthouses. But let's return to your immediate surroundings, to the quiet room where you're listening. Every object around you is a testament to this fundamental division of particles. Your phone or computer, if you have one nearby, operates on the principles of semiconductor physics, where the fermionic nature of electrons is carefully exploited. The electrons in a semiconductor can only occupy certain energy bands, and the gaps between these bands, caused by the exclusion principle, create the electronic properties that make modern technology possible. The LED lights that might be providing your illumination work because electrons, being fermions, must drop from one energy level to another in discrete jumps, emitting photons in the process. Those photons, being bosons, can then accumulate in large numbers to create the visible light you see. It's a beautiful dance between the two families, fermions creating the energy structure, bosons carrying away the energy as light. If you wear glasses, the lenses work because photons, being bosons, can crowd together to form the electromagnetic waves we call light, which then interact with the electrons in the glass, fermions arranged in careful shells around atoms, to slow down and bend, focusing the light to correct your vision. Every reflection, every refraction, every optical phenomenon you've ever experienced is a collaboration between these two fundamental families of particles. Think about a simple rainbow, perhaps one you saw recently after a storm. The white light from the sun, countless photons of all different energies, enters water droplets in the air. The photons, being bosons, can overlap and interfere with each other, creating the conditions for different colours to bend by different amounts. The electrons in the water molecules, being fermions, create the refractive index that causes this bending. Together, bosons and fermions paint the arc of colour across the sky, a masterpiece of quantum collaboration visible to the naked eye. Even something as simple as the warmth of sunlight on your skin is a testament to this division. The photons from the sun, having travelled 93 million miles through the vacuum of space, arrive at your skin where they interact with electrons in your molecules. The photons can arrive in vast numbers, overlapping in space and time because they are bosons. The electrons must each maintain their own quantum state because they are fermions. The interaction between them, boson meeting fermion, creates the sensation of warmth, the energy transfer that powers life on Earth. As we prepare to dive deeper into this mystery, to explore why identical particles must follow these rules, let's take a moment to appreciate the profound elegance of this arrangement. The universe could conceivably have been built differently. We can imagine, mathematically at least, universes where all particles are bosons, or where all are fermions, or where the division follows different rules. But in our universe, this particular division, some particles social, some solitary, creates the rich complexity we see around us. Without fermions and their exclusion principle, atoms would collapse, matter as we know it couldn't exist. Electrons would all fall to the lowest energy state around nuclei, chemistry would be impossible, and the universe would be a very different, much simpler place. Without bosons and their ability to share states, we wouldn't have laser light, wouldn't have the force-carrying particles that mediate fundamental interactions, wouldn't have the possibility of Bose-Einstein condensates and superfluids that reveal quantum mechanics on a macroscopic scale. The interplay between these two families creates the texture of reality. Fermions provide structure, create the scaffolding on which the universe builds complexity. Bosons provide interaction, carry forces and energy, allow different parts of the universe to communicate and influence each other. Together, they weave the fabric of space-time with threads of matter and energy, probability and certainty, separation and unity. Consider the very atoms in your body. Each carbon atom, essential to life as we know it, has 6 electrons arranged in specific orbitals. These electrons, being fermions, fill up the available states according to strict rules. 2 can go in the innermost shell, but they must have opposite spins, a quantum property that provides another way for fermions to differ and thus avoid being in exactly the same state. 4 more go in the next shell, again carefully arranged to respect the exclusion principle. This arrangement isn't arbitrary. It emerges from the fermionic nature of electrons, from the fundamental fact that they cannot share quantum states. And this arrangement determines how carbon bonds with other atoms, how it can form long chains and complex molecules, how it becomes the backbone of proteins and DNA, how it makes life possible. Every organic molecule in your body exists because fermions must keep their distance, must find their own unique quantum states. But life also depends on bosons. The chemical bonds between atoms involve the exchange of virtual photons, bosons that carry the electromagnetic force. The energy that powers your cells comes ultimately from photons from the sun, captured by plants and converted into chemical energy. The thoughts flowing through your brain right now involve electrical signals, which are really flows of electrons guided and controlled by photons mediating electromagnetic interactions. Even consciousness itself, whatever that ultimately proves to be, emerges from this interplay of bosons and fermions. The neurons in your brain fire when fermionic electrons flow through channels, creating currents. these currents generate electromagnetic fields carried by bosonic photons that influence neighboring neurons. The complex patterns of these interactions, billions of fermions and bosons dancing together in intricate patterns, somehow give rise to your awareness, your ability to contemplate these very particles. As you consider these ideas, perhaps adjusting your position slightly to get more comfortable, you're witnessing this dance firsthand. The pressure sensors in your skin work because fermions in the form of electrons maintain specific arrangements in sensor molecules. The signal travels to your brain via the movement of ions, atoms with missing or extra electrons, fermions whose absence or presence changes everything. The sensation you experience emerges from countless quantum events, each one respecting the fundamental division between bosons and fermions. The soft light that might be filtering through your eyelids right now, perhaps from a nightlight or the moon or a distant street lamp, consists of photons that have travelled various distances to reach you. Some might have journeyed just a few feet from a nearby lamp. Others might have travelled from the moon, taking about 1.3 seconds to make the journey. Still others might be from stars, having travelled for years across the void. All of them, being bosons, can overlap in your eye, can crowd together on your retina, can pile up in the same quantum states to create the classical electromagnetic field we perceive as light. If you were to open your eyes and look at that light source directly, though please don't if it's too bright, you would be observing the result of countless bosons working together. In an incandescent bulb, electrons in the tungsten filament, heated by electrical resistance, jump between energy levels, emitting photons. In an LED, electrons drop across a carefully engineered energy gap, producing photons of specific colours. In the sun or stars, nuclear fusion deep in the core creates photons that then spend thousands of years bouncing their way to the surface before streaming across space. All of these photons, regardless of their origin, follow the same bosonic rules. They can overlap, interfere, combine and separate without the restrictions that fermions face. This is why we can have intense laser beams where countless photons march in lockstep, and it's why radio waves can pass through each other without disruption, allowing multiple signals to coexist in the same space. But now let's consider what happens when we try to do the same thing with fermions. Imagine trying to create a fermion laser, where electrons would all occupy the same quantum state. It simply cannot happen. The exclusion principle forbids it absolutely. This isn't a technological limitation that we might overcome with better equipment. It's a fundamental law of nature, as absolute as the conservation of energy or the speed of light. This prohibition has profound consequences. It's why white dwarf stars don't collapse further. The electrons resist being squeezed into the same states. It's why neutron stars exist. The neutrons, also fermions, provide degeneracy pressure. It's why you don't fall through your chair. The electrons in your atoms and the chair's atoms refuse to overlap. It's why chemistry works the way it does, why the periodic table has its structure, why some elements are reactive and others inert. The division between bosons and fermions even shows up in the statistics of how particles behave in groups, which is where the names Bose-Einstein statistics and Fermi-Dirac statistics come from. If you have a box full of identical bosons at a certain temperature, they distribute themselves among available energy states in a particular way, with many particles potentially crowding into the lowest energy state. If you have the same box full of identical fermions, they distribute themselves completely differently, with at most one particle per state, creating what looks like a ladder of occupied energy levels. These different statistics lead to dramatically different behaviours at low temperatures. Bosons can undergo Bose-Einstein condensation, where a large fraction of the particles crowd into the lowest energy state, creating a new phase of matter with strange properties like superfluidity. Fermions at low temperature form what's called a Fermi sea, with particles filling up energy states from the bottom up, like water filling a container, but with each particle maintaining its own unique state. You might wonder why nature chose this particular division, why the universe insists on these two families and no others in our three-dimensional world. The answer, as we'll explore more deeply, seems to be written into the very mathematics of quantum mechanics and relativity. It's connected to deep properties of space and time, to the way rotations work in 3 dimensions, to fundamental symmetries that underlie all of physics. There's something called the spin statistics theorem, proven by Wolfgang Pauli in 1940, that shows that in any reasonable quantum field theory, that respects relativity, particles with integer spin 0, 1, 2, etc. must be bosons, while particles with half-integer spin 1, 2, 3, 2, 5, 2, etc. must be fermions. This isn't an arbitrary rule imposed from outside. It emerges from the basic structure of how quantum mechanics and special relativity fit together. Spin itself is a quantum property with no perfect classical analogue. It's not really about particles spinning like tiny tops, though that's where the name comes from. It's more fundamental than that, related to how particles transform under rotations, to their intrinsic angular momentum. And somehow, through the beautiful mathematics of quantum field theory, this property of spin becomes linked to whether particles are social or solitary, whether they follow Bose-Einstein or Fermi-Dirac statistics. Photons have spin 1, and they're bosons. Electrons have spin 1, 2, and they're fermions. The Higgs boson, confirmed at the Large Hadron Collider in 2012, has spin 0, and true to the theorem, it's a boson. Quarks have spin 1, 2, and they're fermions. The pattern holds perfectly for every particle we've ever discovered. It's as if the universe has a deep rule. Your spin determines your social behavior. But why should spin be connected to statistics? Why should the way a particle transforms under rotations determine whether it can share quantum states with its identical twins? This is one of those places where the mathematics seems to know something profound about reality, where equations discovered through pure logical reasoning turn out to describe the actual world with stunning accuracy. As you lie there, perhaps feeling yourself beginning to relax more deeply, you're surrounded by the evidence of this mathematical truth. Every atom in your body, every photon reaching your eyes, every particle in the air you breathe follows these rules perfectly. There has never been an observation of a fermion acting like a boson or vice versa. The division is absolute, universal, and as far as we can tell, eternal. Think about what this means for the universe as a whole. Every star shining in the night sky does so because fermions in the form of protons resist compression, creating the conditions for fusion, which then releases energy in the form of bosonic photons. Every planet orbits because gravity, mediated by hypothetical bosonic gravitons, allows forces to overlap and combine. Every atom exists because fermionic electrons organize themselves into shells, creating the rich chemistry that makes planets interesting. In distant galaxies billions of light years away, the same rules apply. Electrons are still fermions, photons are still bosons. The division that we observe here on Earth holds true throughout the observable universe. It's one of the most universal patterns we've discovered, a fundamental organizing principle that shapes reality at every scale. Even in the most extreme environments we know of, the event horizons of black holes, the cores of neutron stars, the first moments after the Big Bang, this division persists. Fermions remain fermions, bosons remain bosons. The rules don't bend or break, even when spacetime itself is curved to the breaking point, even when temperatures and densities reach values that dwarf anything we can create in laboratories. This universality suggests something deep about the nature of reality. The division between bosons and fermions isn't just a feature of our particular corner of the universe or our particular moment in cosmic history. It seems to be built into the fabric of space-time itself, a necessary consequence of the way quantum mechanics and relativity interweave to create the tapestry of existence. As we prepare to explore this mystery more deeply, to look at the specific evidence and the subtle mathematics that underlies this division, take a moment to appreciate where you are in this cosmic story. You're a collection of fermions and bosons, arranged in patterns of stunning complexity, capable of contemplating your own quantum nature. The very fact that you can think about these particles, that you can wonder about why they behave as they do, is itself a consequence of their behavior. Your brain, with its 100 billion neurons and 100 trillion connections, is possible because fermions create stable structures, while bosons allow communication between them. Your consciousness, whatever its ultimate nature, emerges from this quantum dance. You're not separate from the universe you're contemplating. You're a particularly interesting arrangement of the same particles that fill empty space and burning stars. And tonight, as you drift towards sleep, you remain part of this vast quantum symphony. The fermions in your body continue their careful dance, maintaining their separate states, building and rebuilding the molecules of life. The Bosons continue their social gathering, carrying forces, transmitting energy, allowing the different parts of your body to communicate and coordinate. Together, they create the ongoing miracle of your existence. Somewhere in the darkness of your room, photons that left the sun 8 minutes ago are arriving, having travelled 93 million miles to bring warmth and light to Earth. Some of them might be reaching you now, gentle infrared photons carrying heat, visible photons creating the soft glow you might perceive even through closed eyelids. They overlap freely, these bosons, creating the classical electromagnetic fields we experience as light and warmth. Meanwhile, electrons in your neurons are carefully maintaining their separate quantum states, their fermionic nature ensuring that each one has its own unique position in the atomic hierarchy. Some are jumping between energy levels, absorbing and emitting photons, creating the electrical signals that are your thoughts. Others are forming and breaking chemical bonds, storing and releasing the energy that powers consciousness. This is the universe you inhabit, not a cold, mechanical cosmos of dead matter and empty space, but a rich dynamic realm where two families of identical particles weave reality through their eternal dance. Bosons and fermions, social and solitary, overlapping and separated, together creating everything from hydrogen atoms to human thoughts, from starlight to symphony orchestras, from the quantum vacuum to the vast cosmic web of galaxies. As we settle deeper into this exploration, let's start with something familiar, something you can relate to from your everyday experience. Imagine you have 2 coins in your pocket, both quarters perhaps, minted in the same year, looking absolutely identical to the casual observer. If you were to take them out and place them on the table beside your bed, you might not be able to tell which was which. They could be perfect twins to your eyes, catching the light in the same way, showing the same profile, the same inscriptions, the same slight wear from years of handling. But here's the thing about those coins. Even if you can't tell them apart, even if no one could tell them apart without sophisticated equipment, they are fundamentally different objects. One coin has been in certain pockets, touched certain hands, perhaps fallen on particular sidewalks. The other has had its own journey, its own history. If we had perfect knowledge, if we could track every atom, we would find tiny differences. A few atoms worn away here, a microscopic scratch there, slightly different arrangements of copper and nickel atoms in their crystalline structure. More fundamentally, even if we could somehow make 2 coins absolutely identical down to the last atom, which we can't, but imagine we could, they would still be distinguishable in principle. We could paint a tiny dot on one, so small you'd need a microscope to see it, but it would be there. We could follow one coin's path through space, never losing track of which one was which. They occupy different positions, and we can keep track of those positions as they move. They are separate objects with separate identities, even if those identities are hidden or difficult to detect. This is how we understand objects in our daily world. 2 identical cars rolling off an assembly line are still 2 different cars. You could follow one to a dealership in California and the other to New York. 2 glasses of water might look the same, but one contains these particular water molecules and the other contains those particular water molecules. Even identical twins sharing the same DNA are clearly different people with different experiences, different memories, different positions in space. This intuition serves us well at the scale of human experience. It's so fundamental to how we think that we rarely question it. Of course, things have individual identities. Of course, we can, in principle, keep track of which object is which. Of course, swapping 2 objects is a real, physical change, even if we can't detect the difference. This is the classical world, the world of our everyday experience, and these rules seem as natural and inevitable as breathing. But now let's descend into the quantum realm and watch how this comfortable intuition begins to dissolve. Consider 2 electrons, not electrons that are similar, not electrons that look alike, but 2 electrons anywhere in the universe. Every electron that has ever existed or ever will exist has exactly the same mass, 909 x 10 just 31 kilograms. Exactly the same charge, negative 1.6 x 10 to 19 coulombs. Exactly the same spin, 1-2 in units where Planck's constant is 1. There are no electron serial numbers, no electron fingerprints, no way whatsoever to tell one electron from another. This goes beyond anything in our macroscopic experience. It's not just that electrons are very similar, like mass-produced items from a very precise factory. They are identical in a way that has no analogue in the classical world. An electron that formed in the Big Bang 13 billion years ago is indistinguishable from one created in a particle accelerator this morning. An electron in your body is identical to an electron in a distant galaxy. There is no test, no measurement, no observation that could ever tell them apart. You might think, well, surely we can tell electrons apart by their positions. This electron is here, that electron is there. And in a sense, you're right. Electrons do have positions, or at least probable positions described by wave functions. But here's where quantum mechanics throws us its first curveball. In quantum mechanics, particles don't have definite positions until we measure them. They exist in states of superposition, spread out as probability clouds, potentially being in many places at once. When we write down the mathematical description of two electrons, we use something called a wave function. This wave function gives us the probability of finding the electrons in various configurations. But because the electrons are truly identical, there's a fundamental ambiguity in this description. If the wave function tells us there's one electron probably near position A, and another probably near position B, which electron is which? The question has no meaning. There is no electron number 1 and electron number 2. There are just two electrons. This might seem like a philosophical nicety, a subtle point that doesn't really matter for practical calculations, but it turns out to have profound consequences. When we write the wave function for two identical particles, we have to account for this fundamental indistinguishability. The mathematics has to reflect the fact that swapping the particles doesn't create a new physical situation. Let me paint you a picture to help visualize this. Imagine you're watching a very slow, very graceful dance performed by two dancers in identical costumes, their faces covered by identical masks. The lighting is dim, atmospheric, making it impossible to tell the dancers apart. They move in complex patterns, sometimes coming close together, sometimes drifting apart, weaving through space in 3 dimensions. Now imagine that at some point in the dance, the lights go completely dark for just a moment. When they come back on, the dancers are in the same positions they would have been if the lights had stayed on, continuing their choreographed movements. But you have no way of knowing whether, during that moment of darkness, the dancers switched places. Maybe dancer A is still on the left and dancer B on the right, or maybe they swapped and now B is on the left and A is on the right. In the classical world, even if you couldn't tell, there would be a fact of the matter. The dancers themselves would know whether they switched. Someone with infrared vision could have watched them in the darkness. Their footprints might tell the tale. But in the quantum world, for truly identical particles, there is no fact of the matter. The situation where they switched and the situation where they didn't are not just indistinguishable, they are the same physical situation. This is where the mathematics becomes beautiful and strange. When we write the wave function for two identical particles, we have to write it in a way that reflects this fundamental ambiguity. If we call the wave function S6, psi, and we label the two particles' coordinates as 1 and 2, then the wave function 6-12 describes finding particle 1 at position 1 and particle 2 at position 2. But since the particles are identical, 6-2.01, particle 1 at position 2 and particle 2 at position 1 must describe the same physical situation. Now, you might think the solution is simple. Just make 6-1 plus 2 equal to 6-2.1. But quantum mechanics is subtler than that. Wave functions are complex mathematical objects that can have phase, like waves in water, that can be at different points in their oscillation. When we swap the particles, the wave function could pick up a phase factor, a complex number that changes the wave's phase, but not its magnitude. It turns out through a beautiful piece of mathematical reasoning that involves the consistency of quantum mechanics and the nature of probability that there are only two possibilities for what happens when we swap identical particles. Either the wave function remains exactly the same, x2.1 nan best 1.2, or it picks up a minus sign, gas-gas-dus-gank-1, gas-gas-pes-gas-nes-dus. These are the only two options that make mathematical sense, that preserve the probabilistic interpretation of quantum mechanics, that keep the physics consistent. Particles that keep the same wave function when swapped are bosons. The mathematical term for this is that the wave function is symmetric under particle exchange. When you swap two bosons, it's like swapping two identical terms in a symmetric equation. Nothing changes. The universe doesn't even shrug, it simply continues as if nothing happened. Particles that pick up a minus sign when swapped are fermions. their wave function is antisymmetric under particle exchange. When you swap two fermions, the wave function flips its sign, like a wave inverting. The probabilities, which depend on the square of the wave function, remain the same. The minus sign squared gives +1, but that minus sign has profound consequences. Let's explore what this minus sign means. Imagine trying to put two fermions in exactly the same quantum state. The wave function would have to describe both particles being in the same place with the same spin, the same energy, the same everything. But if the particles are in the same state, then swapping them doesn't change anything at all. Particle 1 in state A and particle 2 in state A looks exactly like particle 2 in state A and particle 1 in state A. For bosons, this is fine. The wave function remains the same when we swap them, so having both particles in the same state is perfectly allowed. In fact, it's more than allowed. It's encouraged. The mathematics shows that bosons are actually more likely to be found in the same state than in different states, all else being equal. But for fermions, we hit a mathematical wall. The wave function must pick up a minus sign when we swap the particles, but if they're in the same state, swapping them doesn't change anything. The only way to satisfy both requirements is for the wave function to be 0. And if the wave function is 0, the probability is 0. Two fermions simply cannot occupy the same quantum state. This is the Pauli exclusion principle, emerging naturally from the antisymmetry of the fermionic wave function. This isn't a rule imposed from outside. It's not like a traffic law that says fermions must keep their distance. It emerges from the deep mathematical structure of quantum mechanics, from the requirement that identical particles be truly indistinguishable. The universe doesn't have to enforce the Pauli exclusion principle. It's built into the fabric of reality at the most fundamental level. To understand how profound this is, let's return to our everyday world for a moment. Imagine you're organizing a dinner party, and you have identical twins among your guests. Even though they look exactly alike, you can still seat them in the same room, at the same table, even in adjacent chairs. Their similarity doesn't prevent them from being in the same place. You might have trouble telling them apart, but physics doesn't care about your confusion. But if your guests were fermions, if they were truly quantum identical, then the laws of physics would prevent you from seating them in the same quantum state. It's not that they would refuse to sit together out of preference or personality. The universe itself would make it impossible. The probability of finding both fermions in the same state would be exactly 0, as certain as the impossibility of travelling faster than light or creating energy from nothing. Meanwhile, if your guests were bosons, not only could you seat them together, but they would actually prefer it. The more bosons you already have in a particular seat, if seats were quantum states, the more likely additional bosons would be to join them there. It would be like having guests who become increasingly attractive to other guests the more of them gather in one place, creating a kind of quantum party clustering effect. This difference between bosons and fermions shows up in the mathematics in a beautiful way. When we want to describe multiple identical particles, we have to construct the wave function carefully to respect their quantum statistics. For two bosons in states A and B, the wave function is symmetric. Pex A1, B2, please adin 2, B1, 2. The plus sign between the terms ensures that swapping particles 1 and 2 leaves the wave function unchanged. For two fermions in states A and B, the wave function is antisymmetric. Pickers as iridium A kills 1, B turn 2, A-T2, B1, 2. The minus sign between the terms ensures that swapping particles 1 and 2 flips the sign of the wave function. And notice what happens if we try to put both fermions in state. A, the wave function becomes A does 1, A's 2, A's 2, A says 1, 2, 0. The antisymmetry automatically enforces the exclusion principle. This mathematical structure extends to any number of particles. For three fermions in three different states, we need to antisymmetrize over all possible permutations, creating what mathematicians call a determinant. For bosons, we symmetrize instead, creating what's called a permanent. These mathematical objects, determinants and permanents, encode all the information about how identical particles can be arranged in quantum states. The wave function for multiple fermions is called a Slater determinant, named after physicist John C. Slater. It's a beautiful mathematical object that automatically ensures no two fermions can occupy the same state. If you try to put two fermions in the same state, two rows of the determinant become identical, and the determinant becomes 0, probability 0, impossible. For bosons, the situation is reversed. The more bosons you put in the same state, the larger the wave function becomes. This enhancement factor is precisely what leads to phenomena like Bose-Einstein condensation, where macroscopic numbers of bosons crowd into the same quantum state, creating a new phase of matter with remarkable properties. Let's visualize this difference another way. Imagine quantum states as hotel rooms and particles as guests. For fermions, each room can hold at most one guest. Once a fermion checks into a room, that room is off limits to all other fermions. They must find other rooms, even if there are millions of empty rooms identical to the occupied one. It's the ultimate in social distancing, enforced not by hotel policy but by the fundamental laws of physics. For bosons, the hotel operates on completely different principles. Not only can multiple bosons share a room, but the more bosons already in a room, the more attractive that room becomes to other bosons. It's as if the room becomes more comfortable, more inviting, the more crowded it gets. In the extreme case of a Bose-Einstein condensate, millions or billions of bosons might crowd into a single room, leaving all other rooms empty. This difference has observable consequences that we can measure in laboratories. When physicists shoot two identical particles at each other in a particle accelerator, the scattering patterns depend on whether the particles are bosons or fermions. Bosons show enhancement in certain directions. They're more likely to scatter in ways that bring them closer together. Fermions show suppression. They're less likely to scatter in ways that would bring them too close together. In quantum optics, there's a beautiful experiment called the Hong-Ou-Mandel effect that demonstrates bosonic behavior directly. When two identical photons arrive at a beam splitter from different directions at exactly the same time, they always leave together in the same direction. They never split up, with one going one way and one going the other. This is a direct consequence of their bosonic nature, their tendency to bunch together in the same state. For fermions, we can observe the opposite effect. In experiments with ultra-cold fermionic atoms, physicists can watch as fermions arrange themselves to avoid each other, even at temperatures approaching absolute zero, where classical thermal motion has almost stopped. The fermions maintain their separation not because of any force pushing them apart, but simply because of their quantum statistics, their antisymmetric wave functions. The distinction between symmetric and antisymmetric wave functions might seem like a mathematical technicality, but it shapes the universe at every scale. Stars shine because fermions resist compression. Lasers work because bosons like to march in lockstep. Chemistry happens because electrons, being fermions, must arrange themselves in shells around atomic nuclei. Superconductivity occurs when electrons pair up to form composite bosons, suddenly able to share the same quantum state. As you lie there in the darkness, perhaps feeling your breathing slow and deepen, you're experiencing the consequences of this quantum statistics firsthand. The air you're breathing consists of molecules held together by fermionic electrons in specific quantum states. The gentle pressure of the blanket on your skin comes from fermionic electrons in the blanket, refusing to overlap with fermionic electrons in your skin. The warmth you feel radiates from bosonic photons that can overlap and interfere, creating the continuous electromagnetic field we experience as heat. Every chemical reaction in your body right now depends on the fermionic nature of electrons. When ATP molecules release energy in your cells, electrons must rearrange themselves among available quantum states, respecting the exclusion principle at every step. When oxygen binds to hemoglobin in your blood, electrons shift their quantum states in a carefully choreographed dance, each one finding its own unique configuration. Meanwhile, the electromagnetic forces that guide these electrons are carried by virtual photons, bosons that can overlap and combine without restriction. The nuclear forces holding the protons and neutrons in your atomic nuclei together are carried by bosonic gluons and mesons. Even gravity, if our theories are correct, is carried by bosonic gravitons, though these remain theoretical, never yet directly detected. This division between fermions and bosons isn't arbitrary. It emerges from deep mathematical principles, from the requirement that quantum mechanics be consistent with special relativity. The spin statistics theorem, which we touched on earlier, shows that particles with integer spin must be bosons, while particles with half-integer spin must be fermions. This connection between spin and statistics is one of the most profound results in theoretical physics. But why should spin determine statistics? Why should the intrinsic angular momentum of a particle determine whether it's social or antisocial? The full answer requires diving into quantum field theory, into the mathematics of how particles and fields transform under rotations and boosts. But we can get a glimpse of the connection by thinking about what happens when you rotate a particle's wave function. For particles with integer spin, rotating by 360 degrees brings you back exactly where you started. The wave function returns to its original value. This is consistent with bosonic statistics. Swapping two particles twice brings you back to the original configuration, and the wave function should remain unchanged. For particles with half-integer spin, something strange happens. Rotating by 360 degrees multiplies the wave function by 1. You have to rotate by 720 degrees, twice around, to get back to where you started. This peculiar property of half-integer spin is deeply connected to fermionic statistics. The minus sign that appears in rotation becomes the minus sign that appears when swapping fermions. This might seem bizarre. Why should rotating something by a full circle change its sign? But this is one of those places where quantum mechanics reveals that our classical intuitions are limited. In the quantum world, there are more ways to be oriented than just pointing in a direction. The space of quantum states is richer and stranger than the space of classical configurations. As we delve deeper into this mystery, we find that it connects to fundamental properties of space and time. The fact that we live in 3 spatial dimensions plays a crucial role. In a 2-dimensional world, the mathematics works out differently, and particles called anyons can exist that are neither bosons nor fermions, picking up complex phase factors when exchanged. But in our 3-dimensional world, the mathematics is restrictive. Bosons or fermions, plus or minus, social or antisocial, these are the only options. The wave function itself, this mathematical object that encodes all the information about quantum particles, must transform in specific ways under the symmetries of space-time. It must behave properly under translations, moving through space, rotations, turning in space, and boosts, changing velocity. These requirements, when combined with the principles of quantum mechanics and special relativity, lead inexorably to the division between bosons and fermions. Think about what this means. The social behavior of particles, whether they cluster together or avoid each other, is determined by abstract mathematical symmetries. The structure of atoms, the stability of matter, the possibility of chemistry and biology, all flow from the way wave functions transform under rotations. It's as if the universe's operating system is written in the language of group theory and linear algebra, and we conscious beings are running on this mathematical substrate. In the quiet hours of scientific discovery, often late at night when laboratories hum with the soft sounds of equipment and the outside world sleeps, physicists have been gathering evidence for the strange division between bosons and fermions. These experiments, performed with extraordinary care and precision, have revealed the quantum world's hidden rules with stunning clarity. Let's journey now into these moments of revelation, these gentle confirmations of nature's deep patterns. Picture, if you will, a laboratory in Berlin at the dawn of the 20th century. The year is 1900, and physicists are puzzled by a seemingly simple problem. How does a hot object radiate light? They call it black-body radiation, and by all the rules of classical physics, their calculations keep giving impossible answers. According to classical theory, a hot object should radiate infinite energy at short wavelengths. The ultraviolet catastrophe, they called it, a poetic name for a mathematical disaster. Max Planck, working alone in his study, wrestling with equations that refused to behave, made a desperate assumption. What if energy couldn't flow smoothly like water but had to come in discrete chunks, in quanta? It seemed absurd, contrary to everything physicists believed about energy. But when he applied this assumption to the blackbody problem, treating light as though it came in little packets, what we now call photons, the mathematics suddenly worked. The ultraviolet catastrophe disappeared, replaced by a formula that matched experimental observations perfectly. What Planck didn't fully realize at the time was that he had stumbled upon the first evidence for bosonic behavior. Those photons, those little packets of light, could pile up in the same quantum state without restriction. In fact, they preferred to. The more photons already in a particular energy state, the more likely additional photons were to join them. This bunching behavior of photons, this social gathering of bosons, was essential to explaining blackbody radiation. Years passed, and the evidence accumulated like snow on a quiet winter night, each flake adding to the growing understanding. In 1924, a young Indian physicist named Satyendra Nath Bose sent a paper to Einstein, proposing a new way to derive Planck's radiation law. Bose treated photons as indistinguishable particles, counting quantum states in a way that respected their identical nature. Einstein immediately recognized the profound importance of this approach and extended it to matter particles, predicting that at low enough temperatures, bosonic atoms would condense into a single quantum state. This prediction seemed so strange that even Einstein doubted it at times. A macroscopic collection of atoms all occupying the same quantum state. It sounded like science fiction. But Einstein's mathematics was solid, rooted in the fundamental properties of bosons, in their symmetric wave functions and their tendency to cluster together. The prediction waited, patient as a seed in winter soil, for experimental technology to catch up. Meanwhile, evidence for fermionic behavior was accumulating from a different direction. The periodic table of elements, that organized chart hanging in chemistry classrooms around the world, was itself a monument to the Pauli exclusion principle. Why did elements have the properties they did? Why did the first shell of electrons hold only 2 electrons, the second 8, the third 18? The answer lay in the fermionic nature of electrons. Wolfgang Pauli, contemplating atomic structure in the 1920s, proposed his exclusion principle. No 2 electrons in an atom could have the same quantum numbers. They could share 3 quantum numbers, the same shell, subshell and orbital, but they must differ in the 4th, their spin. This rule explained the entire structure of the periodic table, the chemical properties of elements, the very possibility of chemistry itself. Think about what this means. Every time you see a piece of gold gleaming, you're seeing the consequence of fermionic statistics. Gold's unique color comes from relativistic effects on its electrons, but those electrons can only arrange themselves in specific patterns because they're fermions. If electrons were bosons, all of them would collapse into the lowest energy state around the nucleus. Gold wouldn't be gold. Nothing would be what it is. The universe would be a very different, much simpler and certainly lifeless place. The evidence for quantum statistics extends far beyond Earth, reaching into the cosmos itself. In the 1920s and 1930s, astrophysicists were puzzling over white dwarf stars. These stellar remnants, about the size of Earth but with the mass of the Sun, were far denser than any known material. What could possibly hold them up against their own gravity? The answer came from Ralph Fowler in 1926, electron degeneracy pressure. Because electrons are fermions, they cannot all collapse into the lowest energy state, even under the immense gravitational pressure of a white dwarf. They must stack up in energy levels, each electron finding its own unique quantum state. This creates a pressure that has nothing to do with temperature. It comes purely from the fermionic nature of electrons, from their antisymmetric wave functions, from the fundamental fact that they cannot share quantum states. This quantum pressure holds up the star, preventing further collapse. The same principle, applied to neutrons instead of electrons, explains neutron stars. These cosmic extremes, where a teaspoon of matter weighs as much as Mount Everest, exist because neutrons are fermions. The Pauli exclusion principle, written into the fabric of reality at the quantum level, manifests at the scale of stellar remnants, holding up stars against the crushing force of gravity. But let's return to Earth, to the controlled environment of the laboratory, where evidence for quantum statistics can be observed with exquisite precision. In 1987, 3 physicists, Chien-Shiung Wu, Ernest Ambler and their colleagues, performed an experiment that would have seemed like magic to earlier generations. They created a beam splitter for photons, a simple piece of glass that could split a beam of light, sending half in one direction and half in another. When they sent 2 identical photons at this beam splitter from different directions, timing their arrival perfectly so they reached the splitter at exactly the same moment, something remarkable happened. The photons never split up. They always left the beam splitter together, both going the same way. This wasn't a preference or a tendency, it was absolute. When the experiment was done correctly, with truly identical photons arriving simultaneously, they bunched together 100% of the time. This Hongu-Mandel effect, as it came to be known, is a direct consequence of bosonic statistics. The photon's symmetric wave function means that the amplitude for them to exit in different directions cancels out exactly. Only the amplitudes for them to exit together survive. It's as if the universe itself insists that identical bosons stick together when given the chance. For fermions, we observe the opposite behavior. In experiments with ultra-cold fermionic atoms, atoms cooled to temperatures just billionths of a degree above absolute zero, physicists can observe fermionic anti-bunching directly. When two identical fermionic atoms approach each other, they avoid each other, maintaining a minimum separation even when there's no classical force pushing them apart. This isn't because they repel each other in the conventional sense, it's because their antisymmetric wave function makes it impossible for them to get too close while remaining in similar quantum states. In 1995, 70 years after Einstein's prediction, Eric Cornell and Carl Wieman at the University of Colorado finally achieved Bose-Einstein condensation in a gas of rubidium atoms. They cooled the atoms to less than a millionth of a degree above absolute zero, and watched as thousands of atoms suddenly collapsed into the same quantum state. It was as if the atoms had suddenly decided to march in perfect lockstep, becoming a single quantum entity visible to the naked eye, or at least to their sophisticated detectors. This wasn't just cold atoms sitting still. This was a new phase of matter, predicted by the mathematics of bosonic statistics and finally observed in the laboratory. The atoms in a Bose-Einstein condensate lose their individual identities in the most complete way possible, becoming a single macroscopic quantum wave. It's the ultimate expression of bosonic socialism, thousands or millions of particles sharing exactly the same quantum state. The evidence for quantum statistics isn't limited to exotic laboratory conditions. It shows up in everyday technology, in devices you might be using right now. The semiconductor chips in your phone or computer work because electrons, being fermions, fill up energy bands in specific ways. The band gap that makes semiconductors useful comes from the Pauli exclusion principle, from the fact that electrons must find their own unique quantum states. Light-emitting diodes, LEDs, work because electrons and holes, the absence of electrons, recombine in semiconductors, emitting photons. The electrons and holes are fermions constrained by the exclusion principle. The photons are bosons, free to accumulate in large numbers to create the light you see. Every LED is a tiny theatre where fermions and bosons play their appointed roles, following the script written by quantum statistics. Lasers, those remarkable devices that produce pure, coherent light, are perhaps the most dramatic everyday demonstration of bosonic behaviour. In a laser, photons are stimulated to emit more photons in exactly the same quantum state. Same frequency, same direction, same phase. This stimulated emission, predicted by Einstein in 1917, is only possible because photons are bosons. They not only tolerate but actively encourage other photons to join them in the same state. Think about what happens inside a laser. A photon in a particular state passes by an excited atom. The presence of that photon makes it more likely that the atom will emit another photon in exactly the same state. Now you have two identical photons, which make it even more likely that other atoms will emit matching photons. The process cascades, creating an avalanche of identical photons, all marching in perfect synchronization. This is bosonic statistics in action, creating a beam of light with properties impossible in a world without bosons. Superconductivity, discovered in 1911 but not understood until the 1950s, provides another stunning example of quantum statistics at work. At low temperatures, electrons in certain materials can pair up to form Cooper pairs. Two fermions bound together make a composite boson, and these Cooper pairs can all condense into the same quantum state, flowing through the material without resistance. This pairing of fermions to form bosons is a loophole in the exclusion principle, a way for fermions to achieve something like bosonic behaviour. The electrons don't violate their fermionic nature. Each electron in a pair maintains its own quantum state. But the pairs themselves, being bosons, can all occupy the same centre of mass quantum state, creating a quantum fluid that flows without friction. The phenomenon of superfluidity in liquid helium provides yet another window into quantum statistics. Helium-4 atoms having an even number of nucleons are bosons. When cooled below 2.17 Kelvin, liquid helium-4 undergoes a phase transition to a superfluid state. It flows without viscosity, creeps up the walls of containers, and exhibits other bizarre properties that come from macroscopic quantum behaviour. Helium-3, with one fewer neutron, is a fermion. It too can become superfluid, but only at much lower temperatures, below 0.03 Kelvin, and only by forming Cooper pairs similar to electrons in superconductors. The difference in behaviour between helium-4 and helium-3, Two isotopes of the same element differing by a single neutron is entirely due to their different quantum statistics. One is a boson, one is a fermion, and that makes all the difference in the world. In particle physics experiments at accelerators like the Large Hadron Collider, the signatures of quantum statistics are everywhere. When particles collide and produce showers of secondary particles, the distribution patterns depend critically on whether the particles are bosons or fermions. Bosons tend to be emitted in the same directions, creating correlations in the detector data. Fermions avoid each other, creating anticorrelations. These patterns are so reliable that physicists use them to identify particles. If a new particle is discovered, one of the first things physicists determine is whether it's a boson or a fermion. They look at correlation patterns, at how the particle interacts with identical copies of itself, at whether it can occupy the same quantum state as another particle of the same type. The statistics tell them about the particle's spin even before they measure it directly. The cosmic microwave background, that faint afterglow of the Big Bang visible in every direction, carries the imprint of quantum statistics from the early universe. The photons of the CMB are bosons, and their distribution follows the blackbody spectrum that Planck first explained by assuming quantized energy. The tiny fluctuations in the CMB temperature, the seeds from which galaxies grew, were influenced by the interplay between bosonic photons and fermionic matter in the primordial plasma. Even more speculatively, some physicists wonder whether dark matter, that mysterious substance that seems to make up 85% of the matter in the universe, might consist of bosons or fermions we haven't yet discovered. If dark matter particles are bosons, they might form Bose-Einstein condensates on cosmic scales, creating structures very different from ordinary matter. If they're fermions, they would resist compression just like ordinary matter, forming halos around galaxies held up by degeneracy pressure. There's also the fascinating possibility of anyons, particles that are neither bosons nor fermions. In our three-dimensional world, the mathematics restricts particles to being either bosons or fermions. But in two-dimensional systems, which can be created artificially in certain materials, the mathematics allows for more exotic possibilities. Anyons can pick up any phase when exchanged, not just +1 for bosons or 1 for fermions. These anyons aren't just mathematical curiosities. They've been observed in fractional quantum Hall systems, where electrons confined to 2 dimensions in strong magnetic fields create quasi-particles with anyonic statistics. Some physicists believe anyons could be the key to building quantum computers that are naturally protected from errors, using the braiding of anyonic world lines to perform quantum computations. The evidence for quantum statistics extends even to biology. Photosynthesis, the process by which plants convert sunlight into chemical energy, involves the absorption of photons, bosons, by chlorophyll molecules. The efficiency of this process depends on quantum coherence, on the wave-like nature of the energy transfer through the photosynthetic complex. Some researchers suggest that the quantum statistics of the involved particles plays a crucial role in the remarkable efficiency of photosynthesis. Bird navigation might also involve quantum statistics. Some birds seem to navigate using Earth's magnetic field through a quantum mechanical process in certain proteins in their eyes. This process involves pairs of electrons, fermions, whose spins become entangled. The different ways these fermionic spins can combine, constrained by their antisymmetric wave functions, might provide the bird with magnetic field information. As we look toward the future, physicists continue to find new ways to probe and exploit quantum statistics. Ultra-cold atom experiments can now create mixtures of bosons and fermions, exploring how they interact, how they form composite particles, how they organize themselves in optical lattices that simulate exotic materials. These experiments are like miniature universes where physicists can adjust the rules and watch what happens. Quantum computers, those much-hyped devices that promise to revolutionize computation, are essentially machines for manipulating quantum statistics. The qubits in a quantum computer must maintain their quantum coherence, their ability to exist in superposition. For some types of quantum computers, this means carefully managing fermionic or bosonic states, using the statistics of identical particles to perform calculations impossible for classical computers. There's even speculation about more exotic possibilities. Could there be particles that violate the spin statistics theorem under extreme conditions, perhaps near black holes or in the early universe? Could the division between bosons and fermions be emergent rather than fundamental, arising from some deeper theory we haven't yet discovered? These questions remain open, tantalizing possibilities at the frontier of physics, but what we do know, what decades of experiments have confirmed beyond any doubt, is that the division between bosons and fermions is real, universal, and fundamental. Every experiment ever performed has confirmed that particles with integer spin are bosons, and particles with half-integer spin are fermions. No exceptions have ever been found. The pattern holds from the smallest scales we can probe to the larger structures in the universe. As we float deeper into contemplation, let's consider how the quiet distinction between bosons and fermions reaches into every corner of our existence, shaping not just the abstract realm of particle physics, but the very texture of reality you experience every moment. The chair or bed supporting you right now, the air you're breathing, the thoughts flowing through your mind. All of these emerge from the interplay between particles that share and particles that exclude, between the social and the solitary, between waves that add and waves that cancel. Feel the solidity beneath you, the reassuring firmness of matter that holds you up against Earth's gravity. This solidity is not what it seems. The atoms in your body and the atoms in the chair are mostly empty space. The nucleus is a tiny speck in the center, and electrons orbit far away in probabilistic clouds. If atoms were like solar systems with electrons as planets, you should pass right through the chair like a ghost. But you don't, and the reason is fundamentally about fermionic antisymmetry. When the electron clouds of your atoms approach the electron clouds of the chair's atoms, the Pauli exclusion principle springs into action. The electrons cannot occupy the same quantum states, so they must rearrange themselves, finding new configurations that respect everyone's need for quantum personal space. This rearrangement costs energy, creates a repulsive force, gives matter its substance. The solidness you feel is not atoms bumping into each other like billiard balls. It's the manifestation of antisymmetric wave functions, of fermions refusing to share quantum states. Without this fermionic exclusion, matter as we know it couldn't exist. Electrons would all cascade down to the lowest energy level around atomic nuclei. Atoms would collapse to a tiny fraction of their current size. Chemistry would be impossible. There would be no electron shells, no valence electrons, no chemical bonds. The universe would be a very different place, probably just a soup of collapsed matter and radiation, with no complexity, no structure, no possibility for life or consciousness. But the universe gave us both fermions and bosons, and this division creates the possibility for the rich tapestry of existence we observe. Let's explore how this fundamental distinction weaves through technology, philosophy, and our understanding of what it means to exist in a quantum universe. Consider the device you might be using to listen to these words: a phone, a computer, perhaps a smart speaker. Deep within its circuits, billions of transistors switch on and off billions of times per second, processing information, storing memories, connecting you to the vast digital web of human knowledge. Every one of these transistors relies on the fermionic nature of electrons. In a semiconductor, electrons fill up energy bands according to the Pauli exclusion principle. The valence band fills up with electrons, each finding its own quantum state. The conduction band sits above, usually empty at low temperatures. The gap between these bands, the band gap, exists because electrons are fermions. If they were bosons, they would all pile into the lowest available states, and semiconductors wouldn't have the special properties that make them useful for electronics. When we apply voltages to semiconductors, we're essentially controlling the flow of fermionic electrons, exploiting their quantum statistics to process information. Every calculation your device performs, every pixel it illuminates, every signal it sends or receives, depends on electrons behaving as fermions, filling up quantum states according to strict rules that emerge from their antisymmetric wave functions. But bosons play their part too. The information flowing through fiber optic cables travels as photons, bosons that can overlap and propagate together without interfering destructively. The radio waves connecting your device to cell towers or Wi-Fi routers are electromagnetic waves made of photons, taking advantage of bosonic statistics to carry multiple signals through the same space simultaneously. Even more fundamentally, the forces holding the atoms in your device together are mediated by bosons. Virtual photons carry the electromagnetic force between electrons and nuclei. Gluons, bosons with the peculiar property of carrying color charge. bind quarks together inside protons and neutrons. The proposed Higgs boson, confirmed at the Large Hadron Collider, gives particles their mass through a field that permeates all of space. This division of labour, fermions providing structure, bosons mediating forces, seems to be a fundamental organising principle of our universe. It's as if the cosmos needed both types of particles to create the rich complexity we observe. Fermions alone would give us structure but no way for different parts to interact. Bosons alone would give us forces and interactions but no stable structures to interact. Together, they create the possibility for atoms, molecules, chemistry, biology, and ultimately consciousness. Let's dive deeper into the philosophical implications of identical particles and their statistics. In our everyday world, identity seems straightforward. You are you, distinct from everyone else with your own history, memories, and experiences. Even identical twins sharing the same DNA are clearly different individuals. This notion of individual identity is so fundamental to how we think about ourselves and the world that it's hard to imagine reality working any other way. But quantum mechanics tells us that at the fundamental level, identity works differently. An electron in your body is not your electron in any meaningful sense. It has no history, no memory of where it's been. If we could somehow swap it with an electron from a distant star, there would be no way to tell, even in principle. The universe wouldn't notice the swap because there's nothing to notice. The electrons are truly identical. This challenges our notions of what it means to be an individual. You feel like a distinct person, separate from everyone else, with your own unique identity, but you're built from particles that have no individual identity at all. Every electron in your body is identical to every other electron in the universe. Every quark, every neutrino, they're all perfect copies with no distinguishing features. How does individual identity emerge from identical building blocks? This is one of the deep mysteries that sits at the intersection of physics and philosophy. Somehow, the arrangement of identical particles, the patterns they form, the information encoded in their configurations gives rise to the unique individuals we experience ourselves to be. Perhaps identity is not about the particles themselves, but about patterns and information. You're not your atoms. Those are constantly being exchanged with your environment through breathing, eating, and other biological processes. You are the pattern, the arrangement, the information encoded in the configuration of particles. And while the particles themselves are identical and interchangeable, the patterns they form can be unique. This view has profound implications for how we think about consciousness, free will, and the nature of existence. If we are patterns rather than particles, then what persists through time is information rather than matter. The atoms in your body today are almost entirely different from the atoms that were there a decade ago, yet you feel like the same person. Your continuity comes from the preservation and evolution of patterns, not from the persistence of particular particles. The quantum statistics of particles also raises questions about the nature of space and time. Why should the universe care whether particles are bosons or fermions? Why should their behaviour depend on abstract mathematical properties like symmetry under exchange? One possibility is that space and time themselves have properties we don't fully understand, properties that make the division between bosons and fermions inevitable. Some physicists speculate that the three-dimensional nature of space is crucial. In two dimensions, as we mentioned, particles called anyons can exist that are neither bosons nor fermions. In four or more spatial dimensions, the mathematics might allow for even more exotic possibilities. The fact that we observe only bosons and fermions might be telling us something deep about the dimensionality and structure of space-time. There's also the connection to spin, that mysterious quantum property that determines whether a particle is a boson or fermion. Spin is related to rotational symmetry, to how particles transform when we rotate our coordinate system. The fact that particles with integer spin are bosons, and those with half-integer spin are fermions, suggests a deep connection between the geometry of space and the statistics of particles. The spin statistics theorem, which proves this connection, is one of the most profound results in theoretical physics. It shows that in any reasonable quantum field theory that respects special relativity, the connection between spin and statistics is inevitable. It's not a coincidence or an arbitrary rule. It emerges from the deep structure of how quantum mechanics and relativity fit together. This suggests that the division between bosons and fermions is not just a feature of particles, but a feature of space-time itself. The universe comes equipped with two types of quantum statistics because that's what's consistent with the geometry of space and time. It's as if the fabric of reality has two different kinds of threads, and particles must choose which type to be based on their spin. Let's consider how this division shapes the large-scale structure of the universe. Galaxies, stars, and planets exist because fermions resist compression, while bosons mediate attractive forces. Gravity, presumably carried by bosonic gravitons, pulls matter together, but fermionic degeneracy pressure pushes back, preventing collapse, creating stable structures at various scales. In stars, the balance between gravitational attraction and fermionic pressure determines the star's life cycle. In main-sequence stars like our Sun, the pressure comes mainly from hot gas, atoms bouncing around at high speeds. But in white dwarfs and neutron stars, it's purely quantum mechanical, arising from the fermionic nature of electrons and neutrons respectively. This cosmic balance between attraction and resistance, between bosonic forces and fermionic pressure, creates the diverse universe we observe. Without fermions, gravity would collapse everything into black holes. Without bosons, there would be no forces to bring matter together in the first place. The universe needs both to create the rich tapestry of structures we see through our telescopes. Even the possibility of life seems to depend on this division. Life as we know it requires complex chemistry, which requires atoms with electron shells, which requires electrons to be fermions. Life also requires energy flow, information transfer, and the ability for different parts of an organism to communicate, all of which involve bosons carrying forces and energy. Photosynthesis, the basis of most life on Earth, is essentially a device for capturing bosonic photons and using their energy to drive chemical reactions among fermionic electrons. Respiration reverses this process, using chemical energy to pump protons and generate ATP. Both processes depend critically on electrons being fermions that must occupy distinct quantum states, creating the energy levels that make controlled energy transfer possible. The genetic code itself, stored in DNA molecules, depends on the fermionic nature of electrons. The specific shapes of DNA bases, the hydrogen bonds between complementary bases, the entire machinery of genetic replication and protein synthesis, all of it emerges from electrons arranging themselves in specific patterns dictated by the Pauli exclusion principle. Even consciousness, that most mysterious of phenomena, must somehow emerge from the quantum dance of bosons and fermions. Every thought you have corresponds to patterns of electrical activity in your brain, flows of fermionic electrons and ions, guided by bosonic photons carrying electromagnetic forces. The neurotransmitters that jump between synapses are molecules whose shapes and chemical properties emerge from fermionic electrons in specific quantum states. Some researchers speculate that quantum effects might play a direct role in consciousness. Roger Penrose and Stuart Hameroff have proposed that quantum processes in microtubules within neurons might be essential for consciousness. Others suggest that the unity of conscious experience might be related to quantum entanglement, to the way quantum states can be correlated across space. Whether or not consciousness involves quantum effects directly, it certainly emerges from a substrate governed by quantum statistics. The division between bosons and fermions shapes the brain at every level, from the quantum states of individual electrons to the large-scale electrical patterns of neural networks. We are conscious beings built from unconscious particles, thinking thoughts made of particles that cannot think. Let us slow down now, letting the pace of our exploration become even more gentle, more meditative, as we return once again to the central mystery that has been guiding us through this quantum landscape. We come back to the same question, approaching it from different angles like walking slowly around a sculpture in soft light, noticing new details with each change of perspective. Why do identical particles change the rules of reality? Why does the universe insist on dividing particles into these two families, bosons that share, fermions that exclude? We've seen the evidence, we've explored the implications, we've traced the consequences from subatomic scales to cosmic structures. But now, in this quieter space, let's simply sit with the mystery itself, feeling its texture, its depth, its profound strangeness. Sometimes understanding comes not from pushing forward, but from settling back, from letting ideas percolate through consciousness like water through soil, finding their own paths, making their own connections. Picture yourself floating in a vast space filled with particles. Not the harsh vacuum of outer space, but something softer, warmer, more dreamlike. Around you drift electrons, those fundamental fermions that build the architecture of atoms. Watch how they move, how they maintain their careful distances, each one finding its own unique quantum state like dancers who never touch, who maintain perfect spacing even in the most complex choreography. Each electron is surrounded by an invisible bubble of quantum exclusion, not a physical barrier but a mathematical impossibility, a region where no other electron can exist in the same state. These bubbles aren't fixed in size, they depend on the quantum states available, on the energy of the system, on the presence of other particles. But they're always there, these zones of fermionic privacy, ensuring that each electron has its own quantum identity, even though all electrons are identical. Now watch as these electrons approach an atom. See how they arrange themselves in shells, filling up the available quantum states from the lowest energy upward, like water filling a terraced landscape. Two electrons can share the same orbital, but only if they have opposite spins. One spin up, one spin down, finding a way to be different even when they're in the same place. As more electrons arrive, they must find higher energy states, building up the shell structure that makes chemistry possible. This isn't a process that happens once and stays fixed. Electrons are constantly adjusting their states, responding to the electromagnetic fields around them, exchanging virtual photons with the nucleus and with each other. It's a dynamic equilibrium, a continuous dance of fermionic particles respecting each other's need for unique quantum states, while being attracted to the positive charge of the nucleus. We come back to the same question from another direction. Why must electrons behave this way? Why can't they all pile into the lowest energy state like books stacked on a shelf? The answer lies in their wave functions, in the mathematical description of quantum reality. When we write the equation for two electrons, we must antisymmetrize it, ensuring that swapping the electrons introduces a minus sign. This minus sign, this simple mathematical operation, creates all the complexity of chemistry, all the possibility of life. Let's drift now through a different kind of particle cloud, photons streaming from a star. These bosons have no exclusion bubbles, no need for quantum privacy. They flow past and through each other like ghosts, occupying the same space without interference, unless they're specifically set up to interfere quantum mechanically. Watch as millions of photons crowd into the same quantum state, creating a laser beam of unprecedented purity and power. In a laser, we see the opposite of fermionic exclusion, bosonic enhancement. The presence of photons in a particular state makes it more likely that other photons will join them there. It's a quantum peer pressure of the most fundamental kind, not arising from any force or interaction, but from the simple fact that photons are bosons, that their wave functions are symmetric under exchange. We return again to contemplate this symmetry. When you swap two photons in the mathematical description, nothing changes. The wave function remains exactly the same. This seems like such a simple property, almost trivial, yet it shapes the way energy moves through the universe. Every star shining in the night sky, every LED glowing in your home, every fiber optic cable carrying information, all depend on this symmetry, on the bosonic nature of photons. Consider the profound economy of this arrangement. The universe has found a way to encode complex behavior in the simplest possible distinction, symmetric or antisymmetric, plus or minus, bosons or fermions. From this binary choice flows all the richness of matter and energy, structure and force, stability and change. It's as if the cosmos is built on a fundamental yes or no question, asked of every particle: will you share quantum states or not? We come back once more, spiraling deeper. Picture now a Bose-Einstein condensate, that exotic state of matter achieved only near absolute zero. Thousands, millions, even billions of atoms have collapsed into the same quantum state, becoming a single quantum entity visible to the naked eye, or at least to sophisticated detectors. This isn't just cold atoms sitting still. This is matter in its most purely bosonic form, demonstrating what happens when the tendency to share quantum states is taken to its ultimate extreme. In the condensate, individual atoms lose their separate identities completely. You cannot point to one atom and say this one because there is no this one. There is only the collective, the whole, the single quantum wave that encompasses all the atoms. It's the closest thing we can create to a pure quantum object at macroscopic scales, a glimpse of what matter might be like if everything were bosons. Now imagine the opposite extreme, a gas of fermions cooled toward absolute zero. Instead of condensing into a single state, the fermions arrange themselves into what physicists call a Fermi sea. They fill up the available energy states from bottom to top, each fermion finding its own unique quantum niche. Even at absolute zero, where classical physics would predict all motion stops, these fermions maintain their separate quantum states, creating a pressure that comes not from temperature, but from the exclusion principle itself. We return to the mystery from yet another angle. Why should the universe have both types of particles? Why not all bosons or all fermions? The answer seems to be that both are necessary for the kind of universe we inhabit. Fermions provide structure, create the scaffolding on which complexity builds. Bosons provide interaction, carry forces, allow different parts of the universe to communicate and influence each other. Think of it as a cosmic division of labour. Fermions are the universe's architects, creating stable structures, maintaining separations, building the framework of matter. Bosons are the universe's messengers, carrying forces and energy, connecting distant regions, enabling change and interaction. Together, they create a universe capable of both stability and dynamics, both structure and process, both being and becoming. We circle back, approaching from a different direction. Consider how this division manifests in something as simple as the warmth of sunlight on your skin. Photons, being bosons, travel from the sun in overlapping waves, carrying energy across 93 million miles of empty space. When they reach your skin, they interact with electrons, fermions arranged in specific patterns in your molecules. The bosons bring energy, the fermions provide structure to absorb it. Together, they create the sensation of warmth, the flow of energy that powers life on Earth. Every chemical reaction in your body right now is a collaboration between bosons and fermions. Electrons, respecting the exclusion principle, jump between quantum states. Photons carry the electromagnetic force that guides these jumps. The energy levels that electrons jump between exist because of fermionic exclusion. The possibility of jumping at all exists because of bosonic force carriers. It's an intricate dance, choreographed by quantum statistics. We return once more to the question, feeling it deepen with each pass. The division between bosons and fermions seems to be telling us something profound about the nature of reality. It's connected to spin, that mysterious quantum property that has no perfect classical analogue. Particles with integer spin are bosons, particles with half-integer spin are fermions. But why should spin determine statistics? Why should the way a particle transforms under rotations determine whether it can share quantum states? The answer lies deep in the mathematics of quantum field theory, in the way quantum mechanics and special relativity fit together. It's one of those places where mathematics seems to know something about reality that we can barely glimpse. The equations tell us that this connection is inevitable, that any universe with quantum mechanics and relativity must have this division between bosons and fermions. Let's float through this idea slowly, meditatively. Spin is about rotation, about how particles transform when we turn our coordinate system. But in quantum mechanics, rotation is richer and stranger than in classical physics. A particle with spin 1-2, like an electron, has to rotate through 720 degrees, twice around, to return to its original state. This peculiar property, this need for a double rotation, is intimately connected to fermionic statistics. We come back to the same place from another path. When you exchange two particles, you can think of it as a kind of rotation in an abstract space. One particle moves around the other, and they end up swapped. For bosons, this rotation leaves the wave function unchanged. For fermions, it introduces a minus sign. The mathematics of rotation in space becomes connected to the mathematics of particle exchange, and from this connection emerges the division between bosons and fermions. Picture this as a kind of cosmic consistency requirement. The universe must keep its books balanced, must ensure that all its mathematical relationships remain consistent. The way particles rotate and the way they exchange are connected by deep symmetries, and these symmetries allow only two possibilities: symmetric or antisymmetric, bosons or fermions. We spiral. We, inward once more. Consider how this mathematical requirement manifests in the world around you. The chair you're sitting on is solid because electrons are fermions with spin 1-2. The light by which you might be reading comes from photons, bosons with spin 1. The nuclear forces holding atomic nuclei together are carried by gluons, bosons with spin 1. The mass of particles comes from their interaction with the Higgs field, whose quantum is a boson with spin 0. Every particle we've ever discovered fits perfectly into this pattern. There are no exceptions, no violations, no particles that sometimes act like bosons and sometimes like fermions. The division is absolute, universal, written into the fabric of space-time itself. It's as if the universe made this choice at the moment of creation and has never wavered from it. We return to the question one more time, letting it resonate in the quiet space of contemplation. Why do identical particles change the rules of reality? Perhaps the answer is that identical particles don't change the rules. They reveal the rules that were always there, hidden beneath our classical intuitions. The universe has always been quantum mechanical. Particles have always been identical. The division between bosons and fermions has always existed. We just didn't know it until we learned to look closely enough. In our everyday world, we never encounter truly identical objects, so we never see quantum statistics in action directly. Every macroscopic object is distinguishable in some way, carries some history, can be tracked and labelled. It's only when we descend to the quantum realm, where particles have no distinguishing features, that the true rules of reality become visible. And what strange and beautiful rules they are. Particles that refuse to share states, creating the structure of matter. Particles that love to share states, carrying forces and energy. A universe divided into two families, not by decree or accident, but by mathematical necessity, by the deep logic of quantum mechanics and relativity. As we float here in contemplation, surrounded by the gentle mystery of quantum statistics, we can feel how this division shapes everything. Every atom in your body exists because electrons are fermions. Every thought in your mind involves both fermionic electrons and bosonic photons. Every star in the sky balances fermionic pressure against bosonic forces. The entire cosmos is a collaboration between these two families of particles. We come back always to the same profound realization. The universe is not built from stuff in the conventional sense. It's built from identical particles following mathematical rules, creating patterns and structures through their statistical behavior. Matter is not solid in the way we imagine. It's mostly empty space with fermionic particles excluding each other. Forces are not transmitted by invisible springs or fields in the classical sense. They're carried by bosonic particles that can overlap and accumulate. Reality, at its deepest level, is mathematical. The division between bosons and fermions is not a physical split, but a mathematical one, arising from the symmetry properties of wave functions. Yet this mathematical distinction creates all the physical phenomena we observe, from the stability of atoms to the brightness of stars, from the possibility of chemistry to the existence of consciousness. As you lie there in the darkness, perhaps feeling your awareness beginning to soften around the edges, you remain immersed in this quantum reality. The fermions in your body maintain their careful quantum spacing, each electron in its own state, building the architecture of your physical form. The bosons flow through and around you, carrying forces, transmitting energy, enabling the processes of life. You are not separate from the quantum world. You are a particularly interesting manifestation of it. Your consciousness, whatever its ultimate nature, emerges from the interplay of bosons and fermions. Your thoughts are patterns in the quantum dance, temporary arrangements of particles that somehow give rise to awareness, to the ability to contemplate their own quantum nature. And in this contemplation, perhaps we touch something profound. We are the universe understanding itself, quantum particles arranged in such a way that they can think about quantum particles. The division between bosons and fermions, which seems so abstract and mathematical, is the very thing that makes our existence possible. We are here because electrons are fermions, because photons are bosons, because the universe respects the strange and beautiful rules of quantum statistics. In another quiet experiment, performed in laboratories where the hum of cooling systems creates a constant whisper in the background, scientists have been probing even deeper into the nature of quantum statistics. Picture a laboratory at MIT, late on a winter evening, where physicists carefully align lasers and adjust magnetic fields with the patience of craftsmen. They're about to demonstrate something that would have seemed like pure magic just a generation ago. The Hongyu-Mandel effect, one of the most elegant demonstrations of bosonic behavior ever conceived. Two photons approach a beam splitter from different directions. This beam splitter is nothing more than a partially silvered mirror, the kind of thing you might find in a pair of sunglasses, but precisely calibrated to reflect exactly half the light that hits it. Classical intuition would tell us that when two photons arrive simultaneously, there are several possibilities. Both could be reflected, both could be transmitted, or they could split up, one going each way. If photons were like classical particles, like tiny balls of light, we'd expect to see all these outcomes with various probabilities. But photons are bosons, and bosons play by different rules. When the experiment is performed with exquisite precision, the photons must be truly identical, arriving at exactly the same time. Something remarkable happens. The photons never split up. Never. They always leave the beam splitter together, either both transmitted or both reflected. This isn't a preference or a tendency that happens most of the time. When the conditions are right, when the photons are perfectly matched, they bunch together with absolute certainty. The mathematics behind this is beautiful in its simplicity. The amplitude for the photons to exit in different directions, one reflected, one transmitted, cancels out exactly due to quantum interference. Only the amplitudes for them to exit together survive. It's as if the universe calculates all possible outcomes and finds that only the ones where the photons stay together are allowed. This is bosonic statistics made visible, the tendency of identical bosons to congregate written in the language of light. Meanwhile, in another laboratory, this one at the University of Colorado, physicists are cooling fermionic atoms to temperatures that barely exist above absolute zero. They're using a technique called laser cooling, where carefully tuned lasers actually slow atoms down, robbing them of their kinetic energy until they're moving slower than a snail's pace. At these temperatures, the quantum nature of particles becomes dominant, and the effects of quantum statistics become dramatically visible. When they trap fermionic atoms in an optical lattice, a crystalline pattern of light created by interfering laser beams, something fascinating occurs. Even at temperatures where classical physics would predict all motion has stopped, the fermions maintain a minimum separation. They arrange themselves like well-behaved dancers who never touch, each one finding its own quantum state, its own position in the lattice. This isn't because of any repulsive force between them. It's purely a consequence of their fermionic nature, their antisymmetric wave functions that forbid them from sharing quantum states. The experimenters can actually watch this fermionic anti-bunching in real time using sophisticated imaging techniques. They see clouds of atoms that refuse to compress beyond a certain density, that maintain structure even when cooled to temperatures where classical matter would collapse into a featureless blob. It's the Pauli exclusion principle made visible, the fundamental law that keeps matter from collapsing, demonstrated in the controlled environment of an ultra-cold atom trap. These experiments with ultra-cold atoms have opened up entirely new ways to explore quantum statistics. Physicists can now create mixtures of bosons and fermions, watching how they interact, how they influence each other's behavior. They can tune interactions using magnetic fields, effectively adjusting the social preferences of particles in real time. They can create artificial crystals of light where atoms play the role of electrons, but at scales large, enough to observe directly. In one particularly elegant experiment, researchers created a mixture of bosonic and fermionic isotopes of the same element, lithium-6, fermionic, and lithium-7, bosonic. The only difference between these isotopes is a single neutron, but that difference changes everything about their quantum behavior. The lithium-7 atoms, being bosons, can form a Bose-Einstein condensate, all falling into the same quantum state. The lithium-6 atoms, being fermions, cannot condense in the same way. They form what's called a degenerate Fermi gas, filling up quantum states from the bottom up like water filling a container. When these two quantum fluids are mixed, they interact in fascinating ways. The bosons can mediate interactions between the fermions, causing them to pair up and form composite bosons, similar to Cooper pairs in superconductors. The fermions can provide a kind of quantum pressure that affects how the bosons condense. It's like watching two different kinds of quantum matter dancing together, each following its own rules, but influencing the other through their interaction. Let's drift now into even more speculative territory, into realms where experiment gives way to theory, where physicists use mathematics to explore possibilities that we cannot yet test directly. One of the most intriguing ideas is that the division between bosons and fermions might not be as absolute as it appears in our three-dimensional world. In two-dimensional systems, which can be created artificially in certain materials, particles called anyons can exist. These exotic quasi-particles are neither bosons nor fermions, but something in between. When you exchange two anyons, their wave function picks up a phase factor that can be any complex number of magnitude 1, not just +1 for bosons or 1 for fermions. It's as if two-dimensional space allows for a continuous spectrum of quantum statistics rather than just two discrete options. These anyons aren't just mathematical curiosities, they've been observed experimentally in fractional quantum Hall systems, where electrons confined to two dimensions in strong magnetic fields create collective excitations with anyonic statistics. Some of these anyons are even more exotic. They're non-abelian anyons, which means that the order in which you exchange them matters. Swapping particles A and B and then B and C gives a different result than swapping B and C first and then A and B. This property of non-abelian anyons has captured the imagination of quantum computer scientists. If we could create and manipulate non-abelian anyons, we could use them to perform quantum computations that are naturally protected from errors. The braiding of anyonic world lines, the paths they trace through space-time, could encode quantum information in a way that's robust against the environmental noise that plagues current quantum computers. There's something deeply satisfying about the idea that the dimensionality of space determines the types of quantum statistics that are possible. In one dimension, particles cannot exchange positions without passing through each other, so the question of exchange statistics doesn't really arise. In 2 dimensions, we get the rich variety of anyonic statistics. In 3 dimensions and higher, we're restricted to just bosons and fermions. It's as if each dimensionality of space comes with its own rules for how identical particles can behave. Some theorists speculate that in the early universe, when temperatures were extreme and the dimensionality of space itself might have been different, exotic forms of statistics might have been possible. Perhaps in the first fraction of a second after the Big Bang, when the universe was so hot and dense that our normal concepts of space and time break down, particles followed different statistical rules. These primordial statistics might have left subtle imprints on the cosmic microwave background, or influenced the formation of the first structures in the universe. There's also the fascinating possibility that dark matter, that mysterious substance that makes up most of the matter in the universe, might consist of particles with unusual statistical properties. If dark matter particles are bosons, they might form galaxy-scale Bose-Einstein condensates, creating structures very different from ordinary matter. Some theories suggest that ultralight bosonic dark matter could form wave-like structures on cosmic scales, with interference patterns that might be detectable through gravitational lensing. Alternatively, if dark matter particles are fermions, they would resist compression just like ordinary matter, forming halos around galaxies held up by degeneracy pressure. The distribution of dark matter in galaxies might tell us about its quantum statistics, about whether these invisible particles are social or antisocial, whether they share quantum states or exclude each other. In string theory, that ambitious attempt to unify all of physics, the division between bosons and fermions takes on even deeper significance. String theory requires a symmetry called supersymmetry, which relates bosons and fermions, suggesting that every boson has a fermionic partner and vice versa. If supersymmetry is real, and so far there's no experimental evidence for it, then the universe has a hidden symmetry that exchanges bosons and fermions, social particles and antisocial ones. This would mean that the division between bosons and fermions, which seems so fundamental, might be part of a larger pattern that we haven't yet discovered. Perhaps at very high energies, energies that existed only in the first moments after the Big Bang, bosons and fermions were unified in some way, and the division we see today is a kind of broken symmetry, like ice crystals forming from liquid water. Let's return from these speculative heights to more concrete observations. In condensed matter physics, researchers have discovered that the effective statistics of quasi-particles, collective excitations in materials, can be different from the statistics of the underlying particles. For example, in certain magnetic materials, the excitations behave like particles with fractional statistics, even though they're made of ordinary electrons and atoms. This emergence of new statistics from collective behavior suggests that the division between bosons and fermions might not be as fundamental as it appears. Perhaps what we call bosons and fermions are themselves emergent phenomena, arising from some deeper layer of reality that we haven't yet accessed. This is pure speculation, but it's the kind of speculation that drives physics forward, that suggests new experiments and new ways of thinking about the universe. In quantum field theory, particles are excitations of underlying quantum fields. An electron is an excitation of the electron field, a photon is an excitation of the electromagnetic field. From this perspective, the statistics of particles are properties of the fields themselves. Fermionic fields anti-commute. Reversing the order of operations introduces a minus sign. Bosonic fields commute. Order doesn't matter. This field perspective suggests that asking why particles are bosons or fermions is like asking why water is wet. It's a fundamental property of the fields that make up reality. The universe comes equipped with both types of fields because that's what's mathematically consistent, what allows for a stable, causal, relativistic quantum theory. Recent experiments have pushed our ability to observe quantum statistics to new extremes. Using techniques like quantum gas microscopy, physicists can now image individual atoms in optical lattices, watching in real time as they tunnel between sites, interact with their neighbours, and organise themselves according to their quantum statistics. It's like having a microscope that can see the quantum world directly, that can watch bosons congregating and fermions avoiding each other at the single particle level. These experiments have revealed new phenomena that arise from the interplay of quantum statistics and interactions. For example, when fermions interact strongly in one dimension, they can behave like bosons in certain ways, a phenomenon called bosonization. Conversely, bosons with strong repulsive interactions can exhibit fermionic properties, avoiding each other even though their fundamental statistics would allow them to overlap. This blurring of the distinction between bosons and fermions in strongly interacting systems suggests that the division might not be as sharp as it appears in the non-interacting case. Perhaps in extreme conditions, near black holes, in the early universe in exotic phases of matter, the clean separation between bosons and fermions breaks down, replaced by something more complex and nuanced. There's also growing interest in particles that are their own antiparticles, called Majorana fermions. These hypothetical particles, or quasi-particles in certain materials, have properties that make them potentially useful for quantum computing. Because they're their own antiparticles, they have special symmetries that could protect quantum information from decoherence. Some experiments have found hints of Majorana fermions in superconducting nanowires, though definitive proof remains elusive. The search for new forms of quantum statistics continues in many directions. Theorists explore mathematical possibilities, looking for consistent quantum theories with exotic statistics. Experimentalists push the boundaries of what can be created and observed in laboratories, cooling atoms to ever lower temperatures, creating ever more exotic states of matter. Astronomers look for signatures of unusual statistics in cosmic phenomena, from dark matter halos to neutron star collisions. Each new discovery adds another piece to the puzzle, another glimpse of how quantum statistics shapes reality. The Hongu-Mandel effect shows us bosons bunching in real time. Ultra-cold fermion gases show us the Pauli exclusion principle in action. Anyons in two-dimensional systems show us that our three-dimensional statistics aren't the only possibility. Supersymmetry theories suggest hidden connections between bosons and fermions. All of these observations and ideas circle around the same central mystery. Why does the universe organize itself this way? Why are there exactly two families of particles in 3 dimensions? Why does spin determine statistics? Why does the mere fact of being identical force particles to follow different rules? Perhaps we're approaching these questions from the wrong direction. Instead of asking why particles behave this way, maybe we should ask why we would expect them to behave any other way. The division between bosons and fermions might seem strange to us because we evolved in a classical world where truly identical objects don't exist. But from the universe's perspective, from the perspective of the mathematics that governs reality, this division might be the most natural thing in the world. As you lie there in the darkness, surrounded by the gentle hum of technology and the whisper of your own breathing, you're witnessing the ongoing dance of quantum statistics. In every LED that glows, in every transistor that switches, in every chemical reaction in your cells, bosons and fermions are playing their appointed roles. The experiments we've discussed, from the Hongu-Mandel effect to ultra-cold atom traps, are just ways of making this invisible dance visible, of catching glimpses of the quantum choreography that underlies all of existence. Here in the gentle darkness, As you rest with these ideas flowing through your awareness like a quiet stream, let's bring our attention back to something immediate and personal, your breath. Feel the air moving in and out, that ancient rhythm that has sustained you since your first moment in this world. With each breath, you're participating in a quantum dance billions of years in the making, a collaboration between the fermionic matter that forms your body and the bosonic forces that hold it all together. The oxygen molecules you're breathing right now, each one made of 2 oxygen atoms bound together, exist because electrons are fermions. Those electrons arrange themselves in specific molecular orbitals, shared between the 2 oxygen nuclei, but each maintaining its own quantum state, never violating the Pauli exclusion principle. The double bond between the oxygen atoms, strong enough to require significant energy to break, exists because of the specific way fermionic electrons can share space while maintaining their quantum individuality. As these oxygen molecules drift through your lungs, crossing the delicate membrane between air and blood, they encounter hemoglobin molecules waiting in your red blood cells. The iron atom at the heart of each hemoglobin is surrounded by electrons in specific quantum states, creating just the right electronic environment to capture and release oxygen. When oxygen binds, electrons shift their quantum state slightly, changing the color of the hemoglobin from dark to bright red. This color change, visible proof of quantum statistics at work, is why arterial blood looks different from venous blood. But what does it mean that you, a thinking, feeling, conscious being, are built entirely from particles that have no individual identity? Every electron in your body is exactly identical to every electron that has ever existed anywhere in the universe. They carry no history, no memory, no distinguishing marks. If we could somehow swap an electron in your brain with one from a distant galaxy, there would be no way to tell, even in principle. The universe wouldn't notice because there would be nothing to notice. This challenges something deep in our sense of self. You feel unique, individual, separate from everyone and everything else. Your memories are yours alone, your thoughts private, your consciousness seemingly indivisible. Yet you're built from components that are perfectly interchangeable, that have no individuality whatsoever. How does the personal emerge from the impersonal? How does identity arise from the identical? Perhaps the answer lies not in the particles themselves, but in their arrangement, their patterns, the information encoded in their configuration. You are not your electrons any more than a symphony is the air molecules that carry its sound. You are the pattern, the organization, the incredibly complex arrangement of identical particles that somehow gives rise to consciousness, to the ability to think about your own quantum nature. Consider for a moment what this means for the continuity of your identity. The atoms in your body are constantly being exchanged with your environment. With every breath, you release carbon dioxide molecules that were part of you, moments before, and absorb oxygen molecules that become part of you. With every meal, new atoms join the pattern that is you. Over the course of about 7 years, almost every atom in your body is replaced. Yet you feel like the same person, your memories intact, your sense of self continuous. This suggests that what persists through time is not matter, but information, not particles, but patterns. The specific electrons in your neurons right now are different from the ones that were there when you formed your earliest memories, yet those memories persist. The pattern has been maintained even as the substrate has been completely replaced, like a wave that maintains its shape even as different water molecules pass through it. This view has profound implications for how we think about death, consciousness, and the nature of existence. If we are patterns rather than particles, then what exactly ends when we die? The particles don't disappear, they simply reorganize into new patterns. The electrons that once participated in your thoughts will go on to be part of soil, plants, other animals, eventually perhaps other thinking beings. In this sense, the components of consciousness are immortal, even if the specific pattern that is you is not. Some philosophers and physicists have speculated about whether consciousness itself might be a fundamental feature of the universe, like mass or charge. This view, called panpsychism, suggests that perhaps there's something it's like to be an electron, some minimal form of experience associated with even the simplest particles. If this were true, then consciousness wouldn't emerge from unconscious components, but would be a basic feature of reality that becomes complex and integrated in certain arrangements like brains. This is highly speculative, and there's no scientific evidence for electron consciousness. But the question highlights something important about our situation. We are arrangements of quantum particles that have become aware of their own quantum nature. We are the universe looking at itself, studying itself, trying to understand itself. The division between observer and observed, between the scientist and the system under study, becomes blurry when we realize we're made of the same quantum stuff we're investigating. The fact that we can think about bosons and fermions, that we can perform experiments to probe their behavior, that we can build technologies that exploit their properties, suggests something remarkable about the nature of reality. The universe has arranged itself in such a way that it can understand itself, at least partially, through conscious subsystems like us. We are localized patterns of matter and energy that have developed the ability to discover the rules governing all matter and energy. Think about what's happening in your brain right now as you contemplate these ideas. Neurons are firing in specific patterns, sending electrical signals to each other. These signals are carried by ions, atoms with missing or extra electrons flowing through channels in cell membranes. The flow is controlled by voltage-gated proteins that change shape in response to electric fields, opening and closing channels with exquisite precision. Each of these processes depends on electrons being fermions. The specific shapes of the ion channel proteins emerge from the way electrons arrange themselves in molecular orbitals. The electrical signals themselves involve the movement of electrons and ions, fermions that must maintain their separate quantum states even as they flow. The neurotransmitters that jump across synapses have specific shapes determined by electronic structure, by the patterns that emerge from fermionic exclusion. Meanwhile, the forces coordinating all this activity are carried by bosons. Virtual photons mediate the electromagnetic forces between charged particles. If our theories are correct, W and Z bosons mediate the weak nuclear forces involved in certain neurotransmitter interactions. The hypothetical gravitons keep your brain in place, preventing it from floating away. It's an intricate dance of both particle families, working together to create the phenomenon we call thought. But consciousness seems to be more than just electrical patterns in the brain. There's something it's like to be you, a subjective experience that seems to go beyond mere information processing. You don't just process red wavelengths of light, you experience redness. You don't just detect damage to your body, you feel pain. This subjective first-person nature of consciousness, what philosophers call qualia, remains one of the deepest mysteries in science. Some researchers have suggested that quantum mechanics might play a special role in consciousness. Roger Penrose and Stuart Hameroff have proposed that quantum processes in microtubules within neurons might be essential for consciousness. They suggest that the collapse of quantum superpositions in these structures might be connected to conscious moments of experience. This is highly controversial, with many scientists arguing that the brain is too warm and noisy to maintain quantum coherence at the scales necessary for computation. Whether or not quantum mechanics plays a direct role in consciousness, it certainly plays an indirect role through the division between bosons and fermions. Without fermions and their exclusion principle, atoms couldn't exist, chemistry would be impossible, and the complex structures necessary for life and consciousness could never form. Without bosons to carry forces and energy, different parts of the brain couldn't communicate, and the integrated information processing that seems necessary for consciousness couldn't occur. The division between bosons and fermions also shapes our technological extensions of consciousness. The computer or phone you might be using is essentially an extension of your cognitive abilities, allowing you to access information, perform calculations, and communicate in ways impossible for an unaided brain. These devices depend entirely on the quantum statistics of electrons, on their fermionic nature that creates the band gaps in semiconductors that make computation possible. Even our scientific instruments, the tools we use to extend our senses and probe the quantum world, depend on this division. Photomultiplier tubes that detect single photons exploit the photoelectric effect, where bosonic photons knock fermionic electrons out of metals. Scanning tunneling microscopes use the quantum tunneling of electrons to image individual atoms. Laser interferometers detect gravitational waves using the coherent properties of bosonic photons. In a very real sense, we use quantum statistics to study quantum statistics. We exploit the division between bosons and fermions to discover more about that very division. It's a kind of cosmic recursion, the universe using its own rules to understand its own rules. As you lie there breathing slowly, perhaps feeling yourself sinking deeper into relaxation, you can sense how thoroughly you're embedded in this quantum reality. You're not a classical being who occasionally encounters quantum phenomena. You're a quantum being through and through, a pattern of Bosons and Fermions that has somehow developed the ability to recognize itself as such. This recognition brings both humility and wonder. Humility because we realize we're not separate from or above the physical world. We're part of it, made of the same particles that make up everything else. Wonder because the fact that these particles can arrange themselves into patterns capable of consciousness, capable of love and creativity and scientific understanding, seems almost miraculous. The universe could conceivably have been much simpler. If all particles were bosons, matter would collapse, complexity would be impossible, and the cosmos would be a fairly boring place. If all particles were fermions, forces couldn't be transmitted, different regions couldn't interact, and again, complexity would be impossible. But we live in a universe with both types, perfectly balanced to allow for rich, complex, evolving structures. Some see this as evidence for design, for a universe fine-tuned for complexity and consciousness. Others see it as a selection effect. We observe a universe compatible with our existence because we couldn't observe any other kind. Still, others suggest that perhaps all possible universes exist, and we necessarily find ourselves in one that allows for observers. Whatever the ultimate explanation, the fact remains that we are here, conscious patterns of bosons and fermions, capable of contemplating our own quantum nature. We are the universe's way of looking at itself, of understanding itself, of appreciating the profound beauty of its mathematical structure. And perhaps this is enough, to recognize our place in this grand pattern, to appreciate the elegant division between bosons and fermions that makes our existence possible, to feel gratitude for the cosmic accident or necessity that gave us consciousness in a universe governed by quantum statistics. Now, as we move into this quieter space together, let the complexity of what we've explored begin to soften around the edges, like a photograph slowly going out of focus, retaining its essence but losing the sharp demands for attention. Your breathing has probably deepened since we began this journey, your body settling more completely into whatever surface supports you. The quantum dance continues within you, billions upon billions of particles following their ancient rules, but you don't need to track every step. You can simply rest in the knowing that it continues perfect and automatic, requiring nothing from your conscious mind. We've travelled far together tonight, from the familiar solidity of everyday objects to the strange quantum realm where particles have no individual identity, where the mere fact of being identical changes the fundamental rules of behaviour. We've seen how electrons, those quintessential fermions, refuse to share quantum states, building up the architecture of atoms, creating the possibility of chemistry, of biology, of thought itself. We've watched photons, those perfect bosons, crowd together in laser beams and stellar radiation, carrying forces and energy across the cosmos without restriction. Perhaps the details are already beginning to blur, and that's perfectly fine. You don't need to hold on to every equation, every experiment, every philosophical implication. Let them drift like clouds across the sky of your awareness, present but not demanding, visible but not sharp. What matters is not the precise retention of facts, but the gentle sense of wonder, the quiet appreciation for the profound patterns that underlie reality. Think of it this way. Right now, as you rest there in the darkness, you're a living demonstration of everything we've discussed. You don't need to understand it intellectually to embody it perfectly. Every atom in your body knows exactly what to do. Every electron maintains its proper quantum state without consulting you. Every photon carries its portion of electromagnetic force without requiring your permission or understanding. You are the universe expressing itself in human form, and that expression continues whether you're awake or asleep, whether you're thinking about quantum mechanics or dreaming of entirely different things. The division between bosons and fermions that we've explored tonight, it's not something you need to force yourself to understand completely. It's something you are, something you embody, something that expresses itself through your very existence. The fermions in your body are maintaining their careful quantum spacing right now, not because you're thinking about them, but because that's simply what fermions do. The bosons are carrying forces between your atoms, enabling the chemistry of life, not because you will it, but because that's their nature. Let's revisit very gently the journey we've taken, but now with a softer focus, like remembering a dream from last night, the overall feeling more than the specific details. We began by wondering why identical particles change the rules of reality, why the universe insists on dividing particles into two families. We discovered that this division isn't arbitrary, but emerges from deep mathematical principles, from the requirement that quantum mechanics be consistent with the indistinguishability of identical particles. We saw how bosons, with their symmetric wave functions, can crowd together in the same quantum state, creating phenomena like laser light and Bose-Einstein condensates. We saw how fermions, with their antisymmetric wave functions, must each find their own unique quantum state, creating the structure of matter, the shells of electrons in atoms, the pressure that holds up white dwarf stars against gravity. We explored experiments that make these abstract principles visible. Photons bunching together in the Hongou-Mandel effect, fermions maintaining their separation even at temperatures approaching absolute zero. We traced the implications from subatomic scales to cosmic structures, from the transistors in your devices to the fusion in distant stars. But now, as sleep approaches like a gentle tide, these details can recede. You don't need to hold them all in sharp focus. They can become part of the background knowledge of your unconscious mind, part of the deep understanding that doesn't require constant attention. Like knowing how to walk or how to breathe, your knowledge of quantum statistics can sink into the automatic, the assumed, the peacefully accepted. Perhaps the questions themselves are enough for tonight. Why are there exactly two families of particles? Why does spin determine statistics? Why does the universe organize itself this way? These questions don't demand immediate answers. They can float in your awareness like gentle mysteries, invitations to wonder rather than problems to solve. The universe has been following these rules for nearly 14 billion years without needing us to understand them. It will continue following them whether we grasp every detail or simply rest in appreciation of the mystery. There's something deeply comforting about recognizing that the universe operates according to consistent, mathematical principles. Even when those principles seem strange or counterintuitive, they never fail, never take a break, never make exceptions. Every electron in the universe is right now respecting the Pauli exclusion principle. Every photon is following Bose-Einstein statistics. The rules that govern quantum particles are more reliable than any human-made law, more consistent than any machine, more trustworthy than the sunrise. This reliability extends to your own body, your own existence, the quantum rules that keep atoms stable, that allow chemistry to happen, that enable consciousness to emerge. They're not going to suddenly stop working while you sleep. You can let go of any need to understand or control them. They operate perfectly without your intervention, have been operating since before you were born, will continue operating long after you're gone. As your thoughts begin to slow, perhaps becoming more dreamlike and less linear, remember that this too is a quantum process. The neurons in your brain are still firing, but perhaps less regularly, less intensely. The patterns of electrical activity are shifting from the beta waves of alert wakefulness through the alpha waves of relaxation toward the theta waves of light sleep. Each transition involves countless quantum events, electrons jumping between energy levels, neurotransmitters crossing synapses, ions flowing through channels. But you don't need to track any of this. You don't need to understand the mechanism to experience the result. Sleep will come as it always does, carried on waves of quantum statistics that you neither control nor need to control. The Fermions will continue their careful dance of exclusion. The Bosons will continue carrying forces and energy, and you will drift into dreams built from the same quantum processes that build your waking thoughts. Perhaps in your dreams tonight, you'll find yourself floating through clouds of particles, watching electrons maintain their careful distances while photons overlap and interfere. Perhaps you'll dream of being inside an atom, watching the shells of electrons build up according to the Pauli exclusion principle. Or perhaps your dreams will have nothing to do with physics at all, and that's perfectly fine too. The quantum world doesn't require your conscious attention. It continues its dance whether you're watching or not. The profound truth we've touched on tonight, that identical particles must be either bosons or fermions, that this division shapes everything from atoms to galaxies. This truth doesn't need to burden your sleeping mind. It can simply be, like gravity or time, a fundamental aspect of reality that operates whether we think about it or not. You're made of bosons and fermions, You are an expression of quantum statistics, but you don't need to remember this to be it. As sleep approaches, as your conscious mind prepares to hand over control to the deeper rhythms of rest and restoration, take a moment to appreciate the profound beauty of your situation. You're a collection of identical particles that have arranged themselves in such a way as to become aware of their own nature. You're the universe contemplating itself, quantum mechanics studying quantum mechanics, consciousness emerging from the interplay of Bosons and Fermions. This emergence doesn't stop when you sleep. The patterns continue, perhaps differently, perhaps in ways we don't fully understand, but the fundamental quantum processes never pause. Your sleeping brain is still a quantum system, still balancing fermionic structure with bosonic communication, still embodying the fundamental division we've explored tonight. Let the last of your conscious thoughts be gentle ones. You don't need to solve the mysteries of quantum statistics tonight. You don't need to understand why the universe chose this particular arrangement, why spin determines statistics, why three-dimensional space allows only bosons and fermions. These questions have waited billions of years. They can wait until tomorrow or next week or never. What matters is not finding answers, but appreciating the questions, feeling the wonder of living in a universe with such deep and beautiful structure. The particles in your body will continue their dance while you sleep. Electrons will maintain their fermionic exclusion, building and rebuilding the molecules of life. Photons will carry electromagnetic forces, coordinating the countless processes that keep you alive. The division between bosons and fermions will continue to shape reality at every scale, from the quantum to the cosmic, whether you're conscious of it or not. And perhaps this is the deepest comfort, knowing that the universe operates according to principles that don't require our understanding or intervention. We can rest, truly rest, knowing that the fundamental rules won't change while we sleep, that we'll wake to the same quantum world we leave behind when we close our eyes, that the dance of bosons and fermions will continue its eternal rhythm whether we're watching or dreaming. And so, we arrive at the end of our journey, though in the quantum world we've been exploring, endings and beginnings blur together like waves on a quantum sea. Here in the deep quiet of night, with sleep perhaps already tugging gently at the edges of your consciousness, we return one last time to our central mystery. Why do identical particles change the rules of reality? Why does the universe divide its fundamental constituents into bosons that share and fermions that exclude? The question floats now like a leaf on still water, no longer urgent, no longer demanding an answer, simply present in its profound simplicity. We've circled it from many angles, approached it through experiment and theory, traced its implications from the subatomic to the cosmic, felt its presence in our own breathing bodies, and perhaps we've discovered that the mystery itself is as beautiful as any answer could be. Picture the universe in this moment, not just your immediate surroundings, but everything, everywhere, all at once. In distant galaxies, stars are being born in stellar nurseries where gravity pulls together vast clouds of hydrogen, mostly single protons, fermions that resist compression until the pressure and temperature become so extreme that fusion begins. In those same galaxies, other stars are dying, some collapsing into white dwarfs held up by electron degeneracy pressure, others into neutron stars where neutrons push against each other with fermionic stubbornness, refusing to be squeezed into the same quantum state. Between the stars, photons stream through the void, these sociable bosons carrying light and information across billions of light years, overlapping and interfering, creating the vast web of electromagnetic radiation that fills the universe. Some of these photons have been travelling since the universe was only 380,000 years old, carrying the cosmic microwave background radiation, the baby picture of our cosmos, preserved in bosonic waves that can overlap without destroying the information they carry. Here on Earth, in this very moment, trillions upon trillions of quantum dramas are playing out. In every living cell, electrons are jumping between energy levels, absorbing and emitting photons, driving the chemistry of life. In every computer chip, fermionic electrons are flowing through carefully designed channels, their exclusion principle creating the band gaps that make digital computation possible. In every star visible in the night sky, the balance between bosonic forces and fermionic pressure determines whether the star expands or contracts, whether it continues its stable burn or begins its final collapse. And in you, right now, As you lie there in the darkness, both families of particles continue their eternal dance. The fermions maintain the structure of your body, each electron in its proper quantum state, building atoms, molecules, proteins, cells, tissues, organs, systems, all the nested levels of organization that create a human being. The bosons carry the forces that coordinate this vast assembly. Photons mediating electromagnetic interactions, other bosons carrying the nuclear forces that hold atomic nuclei together. This isn't happening because you will it or understand it. It's happening because this is what the universe does, what it has always done, what it will continue to do long after humanity has passed into cosmic history. The division between bosons and fermions is written into the fabric of reality itself, emerging from mathematical principles so deep that we've only glimpsed their foundations. The spin statistics theorem tells us that this division is inevitable in any universe that combines quantum mechanics with special relativity. Particles with integer spin must be bosons. Particles with half-integer spin must be fermions. This isn't an arbitrary rule, but a mathematical necessity, as inevitable as 2 + 2 = 4. The universe couldn't have particles that sometimes act like bosons and sometimes like fermions, any more than it could have circles that are sometimes square. But knowing that the division is mathematically necessary doesn't fully answer our deeper question. Why does mathematics describe reality so perfectly? Why should the universe care about symmetry groups and complex wave functions? Why should physical particles obey abstract mathematical rules? This is perhaps the deepest mystery of all, what physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. Perhaps we're approaching this backwards. Maybe mathematics doesn't describe reality. Maybe mathematics is reality, at least at the quantum level. Maybe particles are nothing more than mathematical objects, excitations in quantum fields that exist in an abstract space of possibilities. When we discover mathematical theorems about quantum mechanics, we're not finding descriptions of reality, we're finding reality itself. From this perspective, asking why particles obey mathematical rules is like asking why triangles have 3 sides. They don't obey the rules, they are the rules, made manifest in forms we can observe and measure. The division between bosons and fermions isn't imposed on particles, it's what makes them particles in the first place, the fundamental categorization that allows discrete entities to exist in a quantum universe. As you drift closer to sleep, perhaps these philosophical questions can transform into something more like poetry, more like music. The universe is singing a song with 2 types of notes: bosonic notes that harmonize and blend, fermionic notes that maintain their distinct voices. Every atom is a chord, every molecule a phrase, every living being a symphony of quantum statistics. You are part of this cosmic composition, not as an audience member, but as part of the performance itself. Your thoughts are melodies played on fermionic electrons jumping between energy levels. Your heartbeat is rhythm maintained by the interplay of bosonic forces and fermionic structures. Your breath is the universe breathing quantum statistics made manifest in the rise and fall of your chest. And when you sleep, the music continues. Different melodies perhaps, different rhythms, but the same fundamental notes, the same division between bosons and fermions that shapes everything from dreams to DNA. Your sleeping brain reorganizes its patterns, consolidates memories, processes the day's experiences all through the dance of identical particles following their quantum rules. In your dreams tonight, you might find yourself anywhere, flying through clouds, talking with loved ones, exploring fantastic landscapes. But wherever your dreams take you, they'll be built from the same quantum foundation we've explored tonight. Dreamlight will still be made of bosonic photons, dream matter will still be built from fermionic electrons and quarks. Even in the most surreal dreamscape, the fundamental rules don't change. There's something deeply comforting about this constancy. No matter how chaotic life becomes, no matter how uncertain the future seems, the quantum foundations remain solid. Every electron will continue to respect the Pauli exclusion principle. Every photon will continue to follow Bose-Einstein statistics. The universe will continue its quantum dance, perfectly choreographed by mathematical laws that never fail. As we reach the very end of our contemplation, let's acknowledge once more the profound beauty of what we've discovered. The universe has given us, or perhaps we should say, the universe has given itself, 2 families of identical particles, perfectly balanced to create complexity and consciousness. Without fermions, no structure. Without bosons, no forces. Without both, no universe as we know it. No stars, no planets, no life. No minds to contemplate the mystery. We are the universe's way of knowing itself. Quantum particles arranged in patterns complex enough to discover their own quantum nature. We are fermions and bosons, organized into scientists and poets, mathematicians and dreamers. We are the cosmos looking in the mirror, recognizing its own reflection, marveling at its own structure. The questions we've explored tonight, why identical particles change the rules of reality, why the universe divides particles into exactly two families, why spin determines statistics. These questions may never have complete answers, but perhaps complete answers aren't the point. Perhaps the point is the questioning itself, the wonder, the recognition that we live in a universe deep enough to inspire such questions. As sleep finally claims you, as your conscious mind releases its grip and drifts into the quantum uncertainties of dreams, remember that you remain part of this vast pattern. The fermions in your body continue their careful dance of exclusion. The bosons continue carrying forces and energy. The division between them continues to shape reality at every scale, from the quantum foam at the Planck length to the large-scale structure of the cosmos. You're safe in this quantum universe, held by forces that never sleep, structured by particles that never forget their nature. The same rules that build atoms and stars build your body and brain. The same division between bosons and fermions that enables chemistry enables consciousness. You're not separate from the quantum world. You are its expression, its embodiment, its way of experiencing itself from the inside. In the silence between heartbeats, in the pause between breaths, the quantum dance continues. In the darkness behind your closed eyelids, particles maintain their eternal patterns. Somewhere in the vast reaches of space, stars are dying and being born, all according to the same quantum rules that govern the atoms in your pillow, the photons from your nightlight, the electrons in your neurons. The universe continues its quiet work, whether we're awake to witness it or lost in sleep. Bosons congregate and fermions exclude. Photons overlap and electrons maintain their quantum privacy. Forces are carried and structures are maintained. The great division we've explored tonight, social particles and antisocial particles, symmetric and antisymmetric wave functions, integer and half-integer spin, continues to shape every aspect of reality. And you, dear listener, you who have journeyed with me through this quantum landscape, you are proof that the universe's arrangement works, that the division between bosons and fermions creates the possibility for wonder, for consciousness, for the ability to contemplate our own quantum nature. You are the universe's success story, a pattern of particles that can think about particles, a quantum system that can study quantum systems. As you drift into sleep, you remain part of this quiet universe, wrapped in its laws, carried by its mysteries gently, peacefully into the night. The questions we have explored will still be here tomorrow if you choose to return to them. The quantum world will continue its dance whether you're watching or not. And you, made of bosons and fermions, structured by exclusion and connected by forces, will continue to embody the profound truth that identical particles change the rules of reality, creating the rich, complex, beautiful universe we call home. Sleep now, knowing that you are held by the same quantum laws that hold stars in their courses and atoms in their orbits. Rest in the certainty that fermions will continue to exclude and bosons will continue to share, that the mathematical poetry of the universe will continue to unfold whether you're conscious of it or not. Dream whatever dreams may come, knowing they too are part of the quantum dance, part of the eternal interplay between matter and force, between the social and the solitary, between the two great families of particles that build reality from the bottom up. And in the morning, when consciousness returns like a tide, when your neurons resume their waking patterns and your thoughts crystallize from the quantum fog of sleep, you'll still be part of this same magnificent pattern. The division between bosons and fermions that we've contemplated tonight will still be there, still shaping everything, still creating the possibility for another day of experience, another chance to marvel at the quantum nature of existence. But for now, rest. Let the universe carry on its quiet work without your conscious participation. Let the bosons and fermions continue their eternal dance while you drift into the peaceful darkness of sleep. The quantum world will be here when you return. Patient as always, mysterious as ever, beautiful beyond words. And as you drift into sleep, you remain part of this quiet universe, wrapped in its laws, carried by its mysteries, gently, peacefully into the night,